recording now. Starting the recording now. Okay, so I have a question. Oh yeah, so I can share the slide. Sure. So okay, so I'll share the slide again. Put the tutorial website. Everything is there. You get access to the first slide, where you can see the link to the code. So here is the website. As I mentioned, you can get the slides. Later on tonight, you get the YouTube video of the presentation, because you might be from everywhere in the world, so it might be pretty late for you. So you can get access to the recording. And this is the agenda for today. So I'll start doing 20 minutes introduction motivation of why explainable AI is pretty important, and what it is, but not only from a machine learning lens, but much broadly in the AI, from an AI angle. And then I'll go a bit deeper on the role of knowledge graph in explainable machine learning. And then that's where we will spend quite some time, is on the tools and coding. So if you're already eager to look at the code, you can go to the GitHub, in the bottom of this presentation here. You can see the link, and there's already some Google Colab. So there's nothing you need to do. You just need to have a Google account, and then just link to the go to the GitHub, just click on the Colab link, and then just run the different cells, and it should be working with no issues on your side. You just need the Google account on your side, and then move to application and lesson learned. So that's the agenda of today, and I'll post the link of the GitHub just here again, if you need it. But then with those two links is exactly what you need. You won't get lost. And just to go through, so here's the GitHub, and you see the different techniques of explainable AI. So I won't go in details now, because it might be not clear for everyone what is what, but you have the different techniques and different way of evaluating explanation. And then you have the different Google Colab accounts. So it's either some I created or some I reuse from other folks. Some here. They're very pretty good work done from different people from MIT, Stanford, and University of Washington, and many others. So I'm reusing and try to make it available for everybody in Google Colab. So let's get started. So I'll give you so that's the outline. Motivations first, and then explainable AI. And you may have seen different tutorials. I think there are many tutorials here. I think at AAAI on that particular topic. But here we really want to go broad first. So really want to give an overview that explanation is not something new and only dedicated for machine learning, but that's required, that's reused, and in many fields of AI. So while natural language processing, but knowledge representation and reasoning, AI planning and scheduling. So, when you submit the papers, there's those different buckets of AI, and explanation is all over the place. So I want just to step back and just show that it's very spreading all over the different fields of AI. Then I'll go a bit more in details on the role of knowledge graph in explainable machine learning. Then on the tools, coding, and engineering practice. So you will see and pretty interesting piece of codes that have been, or libraries that we try to make it working on different use cases. But you will see different way of how you can take some part of the code and how you can reuse it for your own challenge. And then when we move to the coding exercise or the coding practices, there will be machine learning focus. So even if the initial scope is not only machine learning, the coding or libraries available, they are much more focusing on machine learning models. So that's one thing I want to mention, and then move to applications, lesson learn, and research challenges. So that's the agenda for the next 3 hours. It will be slightly more things, especially if you do have questions. So if you think that's long, you can pause. The recording will be on the website at the end of the day. Okay, so let's move to the scope. So okay, sure. Okay, so I did transcription here. Okay, so there's as many interpretation as research angles. So if you look at the recent papers which have been published in different venues, there are many work from many different angles. So the goal it's only 3 hours. So the objective is not really to provide all the content which is available, but try to provide core snippets or core clusters of techniques which have been used for solving different kind of explainable AI challenges. So again, I definitely will miss some. So if you publish papers and I'm not reporting on it, well, I'm really sorry about that, but it's not really aimed at to be an exhaustive list. Otherwise, it will be too much. And you will see towards the end, at least the tools and the venues, the conferences, the workshop, the challenges, and it's huge. The number of those is very large, and keep tracking it. It's a lot. And I'll give you a snippet of what we have seen at NeurIPS in December in 2021. And even at that level, at the one conference level, it's a lot. So and think about many other conferences, AAAI this year, and then NeurIPS is coming, and ICML is coming. There's many new techniques coming in. So it's not aimed at being exhaustive. And explainable AI is pretty broad, so it's covering, it's multidisciplinary because it's aiming at supporting human. It's usually you have HCI and social sciences involved, and you have user interactions, user evaluation, and again, I'm not coming from a social science or HCI perspective, even though I'll show some important factor if we want to move towards real and true explainable AI techniques. I'll touch on those topics, but there's many more work that we may have missed. There's many domain-specific words which are hard to uncover, so sometimes people use different terms and that you might miss, and it's a very niche area, and the terms used maybe root cause analysis, interpretations, and diagnosis, and it's very then specific to the particular work that you're doing. Yeah, so and many papers, yeah, as I mentioned, do not include the keywords explainability or interpretability. So just to give a step back, so explainable AI is really part of a broader vision of what AI should be. If you think about long term and about stakeholders adoptions, business adoptions across industries, it's this umbrella of trustable AI. So any system that embeds models or any algorithms which is built on top of data or built on top of knowledge representations or planning order techniques, they should be trustable. So we should be able to trace the rationale, the reasoning, or the learning mechanism, and people should be comfortable in trusting a system that makes decisions on top of data, on top of whatever reasoning mechanism, and that's the trustable AI dimension. And for reaching that vision, there's a few pillars. So AI need to be explainable. So we need to understand the rationale. They need somehow to be responsible. So if companies getting new systems that's aim at autonomy or make things process autonomous in particular ways, they should be responsible in terms of whatever a charge that they might have. So they may want to not break any ethics or any issues. So that's very important. The validity part, it's whatever you're doing, it's valid. So you really solve a problem, and that solution is valid toward a particular set of properties, and it's possibly preserving. I mean, especially now with the all the data which is leaked in different applications, you want to have models built in a privacy aware way, and you want to have this attached with some kind of explanation. And just to also back up on regulations, so it's not only the the holy grail of getting explanations, regulations, and in California, in Europe, regulators come with some rules, and they try to push particular efforts in having those systems regulated or certified or controlled in some way. So it's getting much more and more popular. So the different continents pushing more pressure on others, so and particular some regions pushing some effort in there. And beyond those charts, it's not only explanation, it's data protections, and it's even going further than that. So that's something very important to be considered. So it's there. People are watching it, and regulators are putting boundaries over it. So it's getting watched. People are watching now the space. So you have a few references here. I won't spend too much time, but that's the different bills or the different regulations that aim at being in place soon, or that need to be enforced. That give you some examples over here. So part one. So let's move to introduction and motivation. So just from a business perspective. So I'm coming from an industry where systems are highly, need certifications. They are highly regulated, and whenever we push an algorithm, it could be an AI algorithm or not, or an AI model or not, it needs to get some proof that it's going to behave as expected, and to capture that this behavior is right. You're tracing based on some tests, and that's what it's giving you, some kind of rationale that it's doing the right thing, and it can be deployed, and then you have some kind of a safety mechanisms to make sure you're making the right thing. If you think about the tech umbrella, so if you think about any data that we do provide as customers to big players like Netflix, Amazon, Facebook, and others, through a screening website or by analyzing cookies, they get a lot of data, and then they make recommendations, they make statistics, and they try to make you the right move in based on what behavior they expect or what they see from your journey in the data world. And then at the end of the day, whenever prediction they're doing, or root cause analysis of something, of things that they're doing, it's ending up making recommendation, for instance, for you. And if that's wrong, so if Amazon make you make the wrong recommendations for buying something, or Netflix making the wrong recommendation on a movie for him to watch, or if a person has been wrongly tagged. I know that the tagging has been disappeared from Facebook, but back then, I mean, that was not the end of the day, right? If the recommendation is not right, the tagging is not correct, you can make mistakes. Even if you get 95% accuracy and you get 95% pleased with the result, this 5%, it's okay, right? And it's not the end of the world. World is keep going. But then if you think about critical systems, this is where I'm coming from, and basically you deploy systems in very critical environments where you try, and here in this context, you try to remove a mine. So you're in a submarine, you need to be very careful about what you need to remove or not, because if you make the wrong move, you may get the mine exploding, and you may have critical challenges. So then when they decide to do something, first it takes time to make the movement and to analyze and to remove if the mine is dangerous here. So if you do decide and that was a wrong decision, then you waste time and you waste energy. And but if you don't make if you make the wrong decisions that it's not a mine and it was, then it could have dramatic effect later on. So that's very dramatic. So then that means if when you make a decision, the operators behind they want to get rational of why this is what it is. So, and that's very important. And they may get different signals coming from multimodal streams, but they want to have this information. So then they kind of trust the systems and they can make the right decision. It's not only the whatever perception task, and then they get the result and that stuff. It's keep going for them. They need to understand, and they need to make sure they do the right thing. The same if we starting. So now we working with a few authorities. So one in Toronto, in trying to making trains a bit more autonomous. So think about pushing machine learning models. There, it's highly regulated. Certification is definitely there. There's very safety concerns, and again, the day we will move with those models fully operated, if something went wrong, again, dramatic impacts. So again, you need mechanisms. Well, if it's not real time, at least for diagnosis and understanding what went wrong, but ideally even real time. So then you can have the human in the loop and making the right decision based on some kind of explanation they may get. But it's not only critical systems, so systems which are deployed on infrastructure that operate live. It's also on software that analyze data, and they try to find this case, the Compass use case that you may have heard a lot, but in the recidivers bias that the system gets. So here, example of changes used from historical data, and where the data was not properly balanced, properly collected. So it was a very long chain of mistakes and on the data, and ending up having an algorithm which was completely biased. So the data was one thing, but also the mechanism of building the model was another dimension, which ending having a black box systems, which ending up making wrong decision here, and which has also dramatic impacts. So it's not critical system, but it's on critical applications here. And then you can move on and move to other applications. The finance domain, it's also a highly regulated context. So credit scoring, loan approval, when decisions are made, they need to be the different companies. They need to make sure that there's a kind of backlog of what decision has been made and how and why, and so then you can keep tracking. So you can't make a system being fully autonomous with no understanding the rationale behind. So having a model, it's getting tricky, particularly in the finance context. So finance it's very important, and particularly 2-3 years ago at NeurIPS. In Montreal, we had the very first challenge on explainable machine learning, and the data was provided by the FICO Institute, which provide the credit scores in US. So that showed that there's strong interest in trying to get a sense of how we can expose and capture explanations among from historical data and it was for loan approval here. And then also, obviously, healthcare. So applying machine learning method in medical care is problematic because of those particular dimensions. So AI should play as the third-party actor in physician-patient relationship, and at the end, you always have the physicians and patients relations, and the AI should be used for helping the conversation. So basically trying to convey what's the rationale between a set of symptoms or behavior of a person's end up to a particular diagnosis, and then what's the rationale. So usually physicians got it. So and the AI system should also provide it. So it's very important and to be very conscious about that. And there's here I mentioned two papers which are very interesting in this particular domain. So if you are much more in the healthcare related domain, I strongly encourage to look at those papers. And the last one, in particular, show some interesting fact about systems providing wrong predictions, and it was not because the model or the algorithm was doing the wrong thing, is because the data collected initially was not right. So it was on trying to understand when you need special care when you do have a symptom of pneumonia, and one of the things that the model captured is that if you do have asthma, which is something touching lungs, and which is very critical, well, particularly if you have pneumonia. So usually you are in a very danger zone if you combine the two. But the system ended up saying if you do have asthma and pneumonia, then you should not be at too risk. And the reason why is because they actually, when they get people with asthma history, they move it to a special units, and they take care of them in a very particular way. And but that information was not captured by some means. So that means that this shortcut was unknown from the systems, and the system made the wrong decision. So if you just look from the angle and you don't know, and here it's something easy for us to understand, but if you think about much more very acronymic like description of disease or symptoms, for us as a non-expert doesn't really make more sense. So you can say, okay, let's trust it, and let's build the model on top of it. And but actually it may have used very critical conclusion out of it. And you do have much more. So and then that's where we're moving slightly to the bias dimension. So you have very great work that make a comparison of different tools back then, so in 2018, much more recently in 2020, on some work that showed that while the data was biased and the model ended up being biased, and then it doesn't perform as expected on some particular. So here we really talk about ethnical and gender. So that's that's something you need to be careful. So that's where you also might need explanation, because that will helping you understanding where you're falling short in subcategories of the data that you have, and it's unfair to treat some of the subcategories of the data in that particular sense. So then that help you maybe clean it, or at least make it better and much more robust to this particular misleaded classes that or class or group of particular people or features that that require much more attention. So that's very important to be considered. So if we look at that explanation definition, so usually in the field, people think about explanations, they use different terms. So here I mentioned only two terms. We took only the Oxford Dictionary definition, but they have much more than those two terms. With those two, you may capture 70% of papers dealing with explainable AI techniques, but you do also have root cause analysis. You do also have diagnosis techniques, and they also capture techniques that relate to explanation. So explanation and interpretation is probably where you find most of it. So usually in the machine learning domain, they use a bit more interpretation, but it's really a mix. And if you look at dictionary definition, explanation is something that you provide to a person so they can understand it. Interpretation is based on your background, how you will interpret whatever information that you get. So if you get an explanation, the system provides an explanation, you could provide these explanations differently to convey the same results. And why you need to convey in different ways is because people have different background and they would interpret differently based on their understanding of the domain. So if I'm a physician I will need a much more detailed description of why I end up with this diagnosis. And I may be okay in having information which is very detailed, but if I'm just the person that received the diagnosis, if you start mentioning too many technical details at the very first go, it might be overloading for the patient who's having the diagnosis. So depending on what kind of information that you have, you might need to get different granularity, and I think it's very important. Usually people think about users and then model to be explained, whatever it's a machine learning model or it's maybe a reasoning model, and then they build an explanation for everybody, but then you need to customize it. I'll go details a bit more where I think exponential should be going. Okay, so there's this source of confusion on what we call black box AI. I think black box AI about usually neural network, but even decision tree, which pretty big and pretty large, might be kind of a black box because it's too specific and you have too many features, and at the end the explanation might be a conjunctions of 50 features with associated values, and that's still confusing. So it does help, but sometimes you do have well nonlinear models that are very difficult to understand. So think about model where you don't necessarily have access to the inside of how the model has been built, and usually people they want to do they want to get a better model. They want to they want to get an understanding, and if you don't provide the right level of information, they won't be able to fine tuning it in a way that's helping them to make it optimal for a particular objective. So, and think also explanation, and that's something I really want to focus is the explanation is something that should be actionable. So usually you put an explanation for something next to be happening, and that something next is because maybe you want the model to be better, maybe you want to debug your model, maybe you want to find bias in the data that you have, maybe you want to fix some part, maybe you want to augment it, maybe you want to make it more robust. There's many things you want to do, optimizations or fixing it, and these explanations might help. So if you provide predictions which might be wrong, and you may get lots of models with wrong predictions, if you get the explanation and say the explanation is not aligned, or it is aligned, but it's something like it's off, it's maybe because of the data that you have, so you might be able to fix it. So that means you correct the real world data, so you need to be careful here. But here, so yeah, so there's plenty of questions people asking, how can I trust a decision? What can I do with it? How do I debug the model? Is it the right predictions? Can I question it? Can you interact with it? So it's a lot of confusion. So it's a lot of work to be done here. So if you think about black box model, so you have the data, you build the model, and you end up with the AI and the predictions, and then you do decision and recommendation. That's usually it. That's it. And there's no really feedback loop. And the explainable AI, it's think about now that you have the data, you still have the model, but it's explainable. And so that means the user, when they get the explanation, they can provide feedback on it. So and that feedback could be, well, it's not normal that the quality of the model is so bad on a particular population, and the explanation might be because of the features which are underrepresented, or maybe some correlation which are found which is not right, and that's because maybe some of the data is missing, and that explanation might be captured and might be reported to the user or to the scientist or the engineers team, and then they can use it, and they can fix it. So, and then you still have the question about up to which level you can modify it. And explanation by design, I think it's very important. It's not you build a model, that's the explanation, that's it. So it's really a life cycle where you do train, you do quality assessment, you deploy, you predict, and the explanation is all over here. So you do train, and then doing training, you can use the explanation for debugging it. The same when you do the quality assessment, the same when you do the deployment. You may learn the data distribution is changing, or maybe you have a concept drift problem. And even better if that's provided by some explanation that highlight and emphasizes this particular need. So the same for prediction. A/B testing also could help. So again, think about, so here it's based on explainable AI. So that's but you can use it for any AI system. But here it's really the explanation is always validated and used for making and moving to the next point. Okay, a few animations. All right, so this one show, and I know it's a fixed picture, but it's the boundaries are not so clear. But that gives you an overview of where are different techniques for building models, here particularly machine learning models, and you can see where they are situated in terms of accuracy, and explainability. And again, don't get this slide too much fixed, because depending on some problems, you may say that's not right. That is not the best. XGBoost is the best. Yeah, you're right. But that's broadly kind of a picture of what's happening usually. So linear model, pretty easy. Usually they're very simple. So you don't have non-linearity, so you don't capture a complex. So when you do have complex data with large number of features, or you need combinations, nonlinear combinations, they won't be doing good. But obviously, if you have very few amount of data and you need a linear model, that might be the best, and you should go for it. So that's why I always encourage, you don't start from the very top. You start with white box model, and quite a few folks in the research community have advocated that don't start with the more complex and fancy architectures to solve your problem. Just take the easy, do the baseline, and then build on top, because you will get explainability for free. So and then as you move much more with complex models, it's much more difficult. Well, especially with neural nets, ensemble methods, it's getting a bit more difficult to get interpreted. But with linear model, it's pretty neat. Decision tree up to a certain level, because of the based on the number of branches and number of features that you may have. So example of the end-to-end XAI system. So I know we haven't detailed the different techniques, but I want just that you get an idea or an overview of what should be an XAI system. Or I like discussing with many different people from the research community, and maybe, obviously also for the industry perspective. And I don't think explainability, especially if you definitely need it. Sometimes you don't need it, so don't get me wrong. Sometimes you just do recommendation. Explanation is maybe not of use, even though you can use it for improving and debugging. Sometimes you don't need it, but when you need it, it's better if it's not a one shot. So it's better if you can do interactions. And here it's a very good example of what's an interactive an explainable AI system, where you detect a particular kind of fish, and there is a classifier, and then you do the classifications, you get the predictions. Usually machine learning systems stop here. Even now, there are more and more libraries on explainable AI when you can easily plug and get saliency maps techniques or super pixels on top of it. But then the next or the ideal pipeline would be a user or maybe a system, questioning, okay, why did you make such a predictions? And then the system should be able to maybe use sensi maps or super pixel regions and say, okay, because those, and here you have the example, green regions arc for fish, while red pushes towards dog. So there's more green. And then the user could keep challenge the system and say, well, actually, it sounds like you're recognizing more the animal texture rather than the fish, and the system might come back and say, well, okay, but here are the examples which are pretty close to it, so I'm quite okay that it's that kind of fish. And then the human can go back and say, but what happens if you remove some part of the background? So that's something that you can use, and then you can get more information. And the system could say, well, I still predict it's fish because of these green superpixels, and keep iterating. And I really think that really at the end of the day, it's you don't provide one explanation, and who is asking is asking different evidence. So some may need more evidence, some need examples, some needs rational from the data itself on the data that you did inference on. So and depending on the use case, you might need different help. So depending on what you want to do, even if it's the same data and maybe you do the same classification task, different users, maybe different outcome that you use out of the data or the result that you get, and you may need much more bulletproof explanation. So and then you can keep iterating. You can even manipulate the data and say, what if I remove just the tail of the fish? For me, it's still a fish. And what if then you say, well, in that case, because I'm maybe working on a fish boat, and on a fish boat you may get some of them with no tails, and you want to make sure that you count all of them, and that's an application. So you can keep asking question and keep asking question. And I think that's a really nice way of articulating and using all the different techniques. And you will see different techniques, so they really example, concept based, science map based, and all could be combined. But and I think now we are at a stage that we have so many different techniques that they really need to be combined, and we need to add the human interaction on the top, so then we can move it much more smoothly towards using the explanation. On the role of data, obviously, well, depending on the data that you have, you will use different techniques. So obviously, if you have an image, it's much easy. It's much easier if you get super pixel. That usually helps to people, even if some recent studies show that well, doesn't really convey the message that it's an explanation. It's just a way of finding what are the most important, but is the most important part of the pictures is the explanation. That's a debate. So and if you think about tabular data, usually you have examples or extract features, but that's the same as images. It's just the nature or the representation of the data is different. So you do also have, well, in terms of evaluation, and I think that I spend a bit of time here because that's where the community have been evolving quite a lot over the course of the last few years, where they were purely, again, looking at from a machine learning angle. So, all right, thank you, Nicolas, for the link on the GitHub. Yeah, and again, if you need access to the link, you can see where I'm presenting on my side. There are the two links here. And again, yeah, so I'll post the slide of the tutorial here for anybody that joined slightly late. Here you are. Okay. Just put it again, just in case. Okay. So yeah, so in terms of evaluation, well, usually from a machine learning angle, perturbation based, you remove features, you get the same results. Okay, good. That means that features was not of any use. Or if you get worse, or removing them is pretty critical. So they might be pretty important. And you try to see where is the mix. So, and then finding correlations, combination of different features that have joint impact. So then here you can see interesting work that they try to understand to which level perturbations, and then try to get well, features that could that you be used for explanation here. And then we move from what I call well, size-based to much more human-based evaluation. So you see much more work. So here I listed the different work that have been done in that direction, and it's very great work. So especially as now more research, more results have been published, you will see much more and more user evaluation, and that's very good, I think. Because the explanation is designed usually for the human. I think towards the end would be a system would be using it and making decision out of what is the explanation. But while you provide an explanation to convince that you're making the right or maybe that you did the wrong move, and to get that rationale, you use that's a human that's here to interpret. And if you just show superpixels or just show features, that's difficult. If you get a much more well, human interactions, it's better to be used. There's a better trust, and that's much more useful in practice. And here I listed a different set of work done by very excellent researchers in the field. And I strongly encourage, if you're interested in the human dimension, human factor in explanation, and we learn a lot. So if you look at the human factors in explanations, so human prefers explanations that are both simple and highly probable. So they prefer causal structure and counterfactual. So you can provide the explanation as an example, but also as a counterfactual. So counterfactual is, what if you didn't get that part? So what if you're not that high, or what if you don't eat such ingredients, or what if you get a higher salary? I mean, what would be the outcome? Will be different. So then I think that resonates a lot with people, because they know what they have, and they know what's missing to reach what they want to get. So if you apply for a loan approval, and that's particularly true. And so in the financial context, where they play a lot with counterfactual, and that's something that people have been using, and a very excellent work on counterfactual explanation from folks from University of Oxford. Larger explanation might push humans into a more careful, rational thinking mode. So obviously, if you provide much more in-depth explanations, well, you spend more time, you start saying kind of very corner cases or edge cases of what the explanation is providing you, and it's not really providing any kind of trust. Okay, so if I move to example-based explanation, so it's better designed for humans. So here you have very good work. So some of the work which have been presented So which have been presented at NeurIPS a year ago, that try to reach, that use the different techniques and try to see what's the impact on the human. And you see, so here on the table on the right, you see different technique, well, different kind of data, so image, text, audio, data, and different techniques. And the last one is the one that provides examples. So it's basically saying, okay, we do this classification on this image because of, and they give you examples that are kind of similar. So they basically try to give you, here are the neighbors of this particular, so that's the way we group. And people tend to prefer those particular explanations. So that this one of the lesson will learn that does provide good, good rationale from the human. They like examples, and I think as soon as you're moving, starting describing features, it's getting more complex. And examples usually do resonate. So well, counterfactual also, but here you see the different examples. And we'll use the code. So I have some Google Colab code that will go through towards the end of the tutorial. So, and again, depending on the data that you have, you might prefer different techniques. So they try different. So that's recent work again, which presented different techniques, and they try with different data, and they learn that based on the data that you were using, sometimes using well, counterfactual was much better. Well, favored in some particular case. So again, based on the data, based on the user, you get different preferences. And the work I presented before was saying example was good for all, but again, depends on the application. So that's something to be careful with. And some recent work I came across is on the saliency maps. So you see a lot of work on well, saliency map using GradCam related techniques that try to find which pixels are important for doing classification. And some folks did some studies and they tried to see if superpixels or saliency map are of use for making a final for understanding the final predictions, and they end up showing that it was not obviously clear that it does help in the user. So here just some thought for you just to think about, well, if we're moving to explanation, say, oh, there are so many techniques doing saliency maps, that should be the way. Again, based on who is your user, what's your applications, what's your data, just ask the user, would that be something useful for you to make to trust the system? So that's something to check. And also the works asking the question, is actually explanation mainly used for debugging, and so then for engineers and making model better, quicker, more accurate, whatever is the metric. And it's very interesting study that show that based on the techniques that you used, that usually we please the engineers. So that's something to be considered, and maybe to please the real end users. And that's something I'm facing well on daily basis. While people they want kind of a story like, and it's not a one shot. So they really need this, I think, multimodal way of providing explanation, or to go a bit more in detail. It's not like a one shot and you're done when you just compute the most important features or the superpixel. That's only the beginning of the explanation story. And then explanation, you have one objective, it's to explain and to clarify a decision made by the system, but you have many, there are many metrics. You can think about the size, so the succinctness, so that's something I mentioned earlier, and now much more the user-based, but also what can you do with it? So that's the actionability, the reusability. So can you reuse the explanation maybe as a feedback for the user to use, and maybe for the model to improve? Can you measure accuracy of the explanation? That's tricky because there's no really one truth of explanation, and it's depending who are you asking, and is it complete? Again, no ground truth. So how can you define that? So they are open questions, so they are not easy questions to answer. And can you easily comprehend? And again, well, a lot of those metrics require the user, and I think it's okay to go on particular applications and provide a framework or a way to articulate different explanations as far as you get the requirements from the user ticked, and that's what we should be doing. It's not a technology for technology. So it's really exposing proper explanation to be actionable and comprehensible in a broad sense. So explainable in AI, so it's not only machine learning. So something I wanted to mention, so so if you submit it to a AAAI, you probably needed to pick one of those topics, and then for the primary topic and maybe subtopic of those. But in all of those, I don't think it was clearly mentioned explanation in all of them. But in all of those papers have been published on those particular topics, or explanation for explaining planning and scheduling, search. This has been done. You have even tutorial on search 10, 15 years ago on the topic, long hours tutorial on explaining constraint satisfactions, on how you can optimize and how you can prune the model. So how you can, and it's not new. The topic is not new. So that and a lot of techniques could be and should be reused in whatever field that you have. I know now machine learning is kind of taking over and over more and more techniques, but sometimes the problem that you may have might be solved by other techniques, and that also have already explanation embedded naturally. So knowledge representation and reasoning is one of those examples. So so machine learning, you have dependency plot, feature importance, surrogate models. They have been coming initially with techniques in those fields, and they're here to help. So usually strongly recommend starting from there. That's if you use the very basic scikit-learn for machine learning, that's there. You can use it. You can and see and have an understanding of what's doing. Obviously, it would be maybe difficult for a human to interpret if your end user is not technical, but that's the very first way to go. In computer visions, I mentioned Salency maps, and you have dozens and dozens of techniques that cover different way of showing superpixel importance. In multi-agent systems, again, many techniques that try to summarize and try to explain how you end up with such an equilibrium in the agent system. So what's the strategy? Because at the end you have agents with conflicting goals, and then when you get this equilibrium, you end up trying to understand why did you end up with such an equilibrium, and that's multi-agent systems. People have been working on that for years. In planning, the same. You try to reach an objective. You have a set of actions. You have initial situations, and you plug those actions together, and why you get a particular plan for solving a goal. There are very important questions to be considered. So that's been studied by a lot of people. Again, in search, I mentioned earlier conflict resolutions. Which constraint you want to relax, and again, if you have a conflicting constraints, explanation is, well, understanding which constraints might be a balance, and that had been studied also well, for years with tutorial back at ICML 10, 15 years ago. Game theory, well, same. Robotics, and that's much more a combination of planning and perception tasks, and even reasoning tasks, and that's when you combine all of them, they also require explanations, and that's much more probably top level, but that does require techniques for providing explanation. Natural language processing, same. Knowledge representation and reasoning, it's naturally embedded in the formalism that they have, as they encode facts in logics, and they combine those facts or those actions to reach conclusion, and whatever conclusion is reached through whatever initial states that you are, and sequences or composition of actions, and this is the natural cause of a goal. So that's the explanation here. Uncertainty in AI, again, it's a great alternative for finding explanation, because you add uncertainty straight in whatever graph that you get, and you try to understand well, causality. So that's the base of explanation here. So if we look at overview of explanation in machine learning, so So you have well, decision trees. This is one of the basic models. That's very easy to interpret, especially if you have limited number of features. That's just if then else statements or a combination of them. And well, basically, if you're fitting that rule, that's it. So you have decision trees and lists, which are kind of similar but in different formalisms, sets, and then you move much more towards linear models, additive models. So then from the top to the bottom, getting more and more complex. So adding much more complexity to the model that you're building or to the interpretation, which make the interpretation much more complex. But there are techniques that you can use for computing models. So you have naive Bayes models. You do have counterfactual. So that's something I mentioned earlier. So there are the naive Bayes models. So that's very with independent conditions, so which makes the problem much simpler, but at least that gives you pretty neat explanation in a very simplistic model. But that's something you can start with. Counterfactual, it's also techniques been used for. And then you have the usual suspect of, as I mentioned, feature importance, partial dependency plot, individual conditional expectations. So you should go towards this list. So that's okay. So now if we move to much more neural net architecture. So what we did is we tried to. So I don't know if you attended NeurIPS, but NeurIPS is one of the core conference on neural architectures, and well, it's bigger than that now, but it's a big event. And I try to find where papers, what kind of work people are doing in the explanation interpretation. And you see the different groups. So here the gray dots are papers, and the red ones are papers with explanation related contributions. And you can see the 2021 trends, so which is actually the 3 months ago trends in AI or at NeurIPS, that show where papers getting published in the field. So TLOR is trying to get explanation on NLP language models, autoencoders, clustering is getting more attention, reinforcement learning, and you see on the left and the right, it has use different terms, so interpretation, explanation. But do you get a sense of what people are doing in the machine learning community? So if we look at artificial neural network, you have the integrated gradients. So I think this is one of the foundations from a neural net standpoint. So that's really where you try to get contributions based on the gradients, so through back propagations, and understand up to the inputs what's the most contributing pixels. So that's integrated gradient based. You have QuadChem and others which are kind of similar flavor, slightly different technically with slightly different result, but it's one of the foundational work from the neural net architecture's perspective. Still in the neural net, you do have example based. So I mentioned it, and that's very great work, where they try not necessarily to find example, but at least to find prototypes. So prototypes is kind of a group of examples. So it sounds like so here in this example where you see dogs, it sounds like it's not a particular breed, but a combination of breeds. And that's what explanation here is really providing prototypes and example. you do have attention mechanism. So with the extension or with all the work on transformers, attention mechanism, you see the great work which has been done on language models, and attentions mechanisms can be used for doing interpretation. And well, it can be used. So I mentioned those work when they show it could be used for explanation, or sometimes I think it's still under discussion. The people are they still trying to make the connection between them. Okay, just looking at the chat. So the question, will the recording be available? So yeah, so that's under recording right now. I'll be posted online on the website that you see on the chat now. Well, later on tonight when the tutorial is done. I know, because it could be pretty late in some location now. So other kind of techniques are interpretable units. So that's some work from MIT where they try to see, based on the architectures that you have, all the neurons, the layers, they try to see which neurons, which units is really responsible for what kind of class. So so it's a segmentation task, and they have a nice way to evaluate the interpretation. It's based on intersection over union, based on the image that you pass as in and the activation that you get for different units. And then the higher you activate, the better it is. And then they really label units in the neural net architectures. And that's why here you see a ResNet unit 924 in 5 channel. I think it should be probably layer 4. Yeah, so that's give you example of which units is responsible for. Still on silency map features on the bottom part, you see the different techniques. Here it's you see it's a paper from 2018. You have even more work that have been published with a long tail of different techniques, and really ranging from like gradient, smooth grad, deconvnet, pattern attributions, and many others. Some are even combining the two. So I mean, you can get pretty exotic on the technique that you're using, and but then the question is still, well, how do I perform on this? It's still well, it's still debating, because there's no really ground truth of which area of the image that you should be focusing on. And then you have some work on visual inspection. So here they provide a textual explanation, but it's much more a classification task where you have the image and the description, and they try to try the description of the image. So, but that's something you could expand to how you construct a textual based explanation. So that will even going further. Some recent work, as I mentioned, you can even combine. So the slide before show, here on the bottom, you see the different techniques. And here, as I mentioned, recent paper here at NeurIPS, so 3 months ago, they mentioned some work where they try well, different techniques, and they end up actually finding different superpixel dimensions or parts, and actually they learn that the best way is actually to combine them, and it's and they have a nice algorithm for finding the right regions and recombining the different techniques. So it's a very computational expansive process. So they use some beam search technique, and they try to find a minimal sufficient explanation. And that's very interesting work, where they're moving towards only finding one technique, analyzing the gradient and doing many fancy things on the gradient. Now they combine them. So it sounds like, as I mentioned, the multimodal is kicking on as well here, not from a multimodal dimension, but much more from a combinatorial dimensions of starting combining techniques rather than only using one. And that's I think that's a good signal that explanation is not one shot, it's combined, and you can combine them. Some work on the uncertainty, again, some work published at NeurIPS 3 months ago, where they try to see, again, when you get explanations, there's a level of uncertainty. I mean, the more, usually the more inputs you get, the better. And usually you do some kind of perturbations, but the perturbations might be statistically realistic or not. So the more perturbation you do, the more realistic you are. And what it shows is if you do the perturbation largely enough, you remove the uncertainty, and basically you increase the explanation scope somehow. And it's basically show that this kind of perturbation sampling, it's pretty important, and it's very important for the stability and the credibility. Because if you don't do it right, and actually many it's an hyperparameter that you tune in most of the techniques. Usually nobody will be touching it, but you should, because it's as they mentioned, it has an impact on stability and the credibility. So that means if you don't touch it and you make it the uncertainty pretty large, when you deploy it, you get explanations which are not they're not rational, or so it's much better to change and to tune that particular set of parameters and to make it much more robust to the uncertainty. And that's very important. So here we really think about the explanation uncertainty. And still in the uncertainty space, some work on explaining uncertainty. So here they took not the challenge of predicting why you get something, or if it's image classification, why you get a particular class. So they don't use counterfactual. So what if you would change? They're using, okay, so they could be classified, and then when you do classification, you have the logit at the end, and the probability distribution, and they say, okay, you get maybe 80%, and so rather than saying that's 80, what's the explanation? They say that's 80, that's 10, and that's 10. Okay, but why do you have this uncertainty? I mean, if you have those two tens, that means that maybe there's some part of the image is toward this particular class. And here they try to say, okay, so let's play with those while marginal but still important class results, and try to see why we get this uncertainty. And for instance, in the context of NIST, 8 and 6, you have uncertainty. So here, the example of the 6, you see the 6, the one closing the loop of the 6 is going towards the 8, and that's where you do have the uncertainty, and that's where when you do classification, and if you look at the CVPR pixel responsible for those, that would be the one closing it. So that's, say, okay, that's an A, but if there's better attention in here, that should be actually an 8. So, and I think that's very interesting work, because they really now caring about okay, why this is right, but what it might be wrong. So so nice work presented at ICLR last year. And here I have a slide. So I'm not describing it full. It's emerging a lot. It's the concept of explanation in knowledge graph or graphs. Well, usually it's graph, it's not necessarily knowledge graph, because there are many work that you can model as a graph. And then when you model it as a graph, you may want to predict a class of a node. You may want to predict connection between nodes. So there are different objectives you want to do. And a lot of machine learning tasks could be adapted to a graph, a graph problem. And then in this concept, then you have the question of how can I use the graph structure to expose explanations. And so here I listed the most well-known techniques. So GNN explainer is one of them. PGM explainer, it's another one. Counterfactual explanation, graph explanation is an interesting one. So what if you have this extra connection? So, and they try to see what you need to add to get that result, but in a much more graph settings. and you do, and it's, and a lot of those techniques, not the one I mentioned here, but a lot of techniques I mentioned earlier on integrated gradient and GradCam, they're based on neural network. Usually when you have a graph, you can build a graph neural network, and then you can apply the classic integrated gradient or gradient-based explanation techniques. And here is the table of the Facebook Captain library, which lists a lot of different techniques that are ready to be used. So here it is the link. I think it's linked to a Google Colab, where you can do explanations on top of a graph. So you will build a model. It's pretty simple one, and then you get the explanation, and then you can change the different techniques. But here it will just show that you can easily do it on graph. And then yeah, and then recently also other techniques called subgraph X that try to extract subgraph. So yeah, so I think it's an interesting field. A lot of data could be captured as graph, and explanation could be extracted. So that's kind of the state-of-the-art techniques that are relevant here in the field. And then we're moving towards something which is slightly more semantic. So rather than having only abstract representation, you try to have labeling or semantic representation, and you have those techniques from pretty good techniques from the TCAV or the ACE tool from Google. You have also the concept shape work. They really try to capture what's the concept captured, and so it's kind of a super pixel based representation, but it's now coming up with a label or with a description, and that's much more useful, because now you can apply techniques that can consume text or representation in a way. So pretty useful. So I strongly encourage to look at that work. If you're much more in understanding the inside of the neural network, this work on circuits, there's a library called Lucid, which is pretty neat. Some work from OpenAI called Microscope, where you can understand, you can go in most of the well-known deep neural net architectures trained on ImageNet data, even bigger. I think they even have the clip. I think they even have the I think they even have the clip. I'm not sure. I think the clip architectures, where you can try and see what kind of motif or representation is in the neuron. So if you remember the MIT paper I showed earlier, you get the unit and you get that representation of the units, and you get the label. And now here, if you use the Lucid, you can have a nice representation of what this unit is abstractly capturing. So you need to be a bit open in terms of visualization, but it's pretty neat in terms of what you can capture. And some years, some work at NeurIPS, I think a year ago, called compositional explanations, which is built on top of the MIT papers, which now try not only to label a neuron, but they try to find a compositional description of a neuron. And what their thesis is, a neuron should not be only one label. There might be a composition of negations, conjunctions, and disjunction of neurons. And the assumption is that you could compose labels, and actually an image is more than one thing. I mean, especially when you think about segmentation tasks, right? An image could be captured and represented in different ways. So they try to have a neuron, say a neuron might be capturing many different things. And that's some of the work which have been doing by some folks from MIT and Stanford. Okay, so here it's much more work on game theory. So from now on, there is a few work on different area of AI. I'll go quickly. You have the reference, because I really want to spend some time on the code, and it takes quite some time. So I want to make sure I'm covering it. But here, today's work on game theory that's been used for solving some machine learning tasks. It's Shapley techniques, one of the probably most well-known and most used techniques for explanation in the machine learning context, but it's coming from a game theory perspective. They had extensions depending on the structural constraints of the data that you have, and they come up with different techniques. Another importance factors, as I mentioned, in search and the constraint satisfaction, that's where you do have constraints among different entities and nodes. And the question is, what are those soft constraints that might be removed, and what I could gain out of it? So that's been work studied for years. I mean, well, 15 years ago with tutorial on the topic. So if you on search and constraint satisfaction, a lot of work on trying to rebalance and resolve conflicts that provide explanations on the shelf with the technique. On knowledge representation and reasoning, you do have a lot of techniques that do diagnosis, justification, the kind of terminology which is used for providing explanation in much more in logic terms. So and the explanation is basically the chains of axioms and facts which are combined together to reach a conclusion. There's also abductive reasoning technique. There are contractions and diagnosis, so they're very specific terms, but it's much more coming from a logic dimensions. In the multi-agent systems, also plenty of work for understanding how you end up with an equilibrium in the agent strategy on the environment. How did you end up with such a system where you do have so many conflicts? So, well, is there a way you can compute summarizations? And there have been work on this particular topic, and also work on explainable agents. So there have been some work in this domain. NLP, well, again, I mentioned attention mechanism, but there are techniques like line could be used. Yeah, there are techniques and tools, NLP debugger, helping understanding attentions between terms. So again, can you use attention mechanisms as an explanation? To be used as a buffer, I think there's kind of you need to be careful about the interpretation that you're doing, but it's a good start. And argumentation and explanation still in the NLP space, pretty neat work too here. And planning and scheduling. So so when you do planning, you analyze the search space. Well, you build this set of actions, or those parallel plans, or whatever composition plans, and then the way you build it, it's those kind of explanation, and then how you can, if something went wrong, what might be the next step that you'll be doing, and then you can get a nice stream of explanations when things go wrong. So I think it's also pretty neat, and that's a very interesting topic. So there's some very recent work at NeurIPS this year on this particular topic, when they try to do well explanations on a navigation system, so that required some planning, and they mentioned kind of the rationale of the system to navigate and to say which goal have been used, under which conditions, what would have been the alternative, and that's a nice thing. It's a nice interactive way of providing some kind of explanation, and that's pretty interesting. Robotics, I mentioned earlier, it's combination of fields here. So it's really something that you need from any angle of AI, from planning, reasoning, machine learning, scheduling. So that's it's kind of a mix. So when you make a decision, you sense your environment, and the explanation is coming from the different sense that the result or outcome of the sensing that you get. And here example of in a robotic context. So it's 5 years old work, but it shows kind of the feeling about what we expect from a human. So they mention which action has been used, and the human is challenging it. So that's a nice way to understand the flow. So here it's a much more in the chatbot like presentation. But you can think about a much more complex and multimodal environment where the robot might show pictures. I turn left because of this obstacle, and it showed the pictures, and then I heard a voice, so I could not go right because of and that maybe they show stairs, and you can see as a much more appealing explanation. And then you have all the work on reasoning and uncertainty, where you do combine knowledge learned from data and knowledge from expert, and you try really to recombine this as a causal graph, and try to recombine and compute explanation and on such a big, large probabilistic graphical model. So that's some of the work has been done in this field. Okay, so I'll just pause 10-20 seconds if there are questions, because we're moving to the next part, and we're nearly halfway. So I'll just pause, just check if there's any. Okay, yeah, you can start shooting with comment or question, and I'll start answering it. So please go ahead. Or thank you, Sasha. So yeah. Okay, so question. Okay, so I have one from Sasha. So often there are many explanations for the same decision. That's right. Yeah. What principles are there to guide which explanation human might prefer? So depends. Depends what's your goal. Depends what are the users that you have. So usually you ask the users, okay, here is the task, or describe me your task, describe your task, the task, and then they say, okay, here based on the task, this is what we can build, and this is what will be the outcome. And then based on our understanding of what can be brought as an explanation, we can say, here is a kind of an example of explanation that you get is based on examples. It's based on well, you have different way of representing it, and then the user should guide you in terms of what it's not about preference, but what is really helping him making the better decision for him. So sometimes it's about preference, but it's also about what's the end goal. And some explanations are most suitable for some users. And again, maybe for the same task and for the same stakeholders, people might prefer different ones because it resonates more. Maybe they have an engineering background, they do have understanding, and they might need that level of details. Well, maybe they're not. So, and again, interpreting your questions, I will interpret in two ways. The first one is, what's the medium I'm using as an explanation? So it's just I'm using different techniques, but the rendering is different. Or I'm using the same rendering, but the explanation is still different because I'm using different techniques, so I'm using different granularity. And here, coming back to the example of personalization, if you use pure text, so let's say you have a technique that explains in pure text, in pure words, what's the rationale of the system to make a decision. If you do have such a system, you may provide some much more customized descriptions for particular users, because that will resonate more. You will need more details, or you might need more abstraction. So here I would see, yeah, two ways. So usually I'll make the user facing the different result that they can get. They don't care about the techniques, they care about the outcome and what they can action out of it. So show them this outcome, and try to see what really resonate and what kind of decision they make. And then when you have one or maybe many, and that's ideally it should be more than one, then go on those and just show that based on those you can still personalize those explanations. And then, and before doing a personalization, I'll show the result based on different techniques, because even if you use one medium or multiple, you can use different techniques to get different results, and some might resonate more. So then show, okay, based on those, which one do you think is the best? I mean, you're the expert. Which one makes you make a quicker decision, an educated decision? Which ones? And then when you get that, then that will be helping the user making the right decision, and you making the right selection of the techniques. I hope that helped. So I have another question from Bart. So as a human, the explanation to why a fish looks like a fish would be, it has fin, it's in water, it has eyes. How far are we from algorithm providing such explanations? Is there any work in this direction? So that's a great, so if you look at the examples I showed earlier on the concept-based explanation, so I mentioned the work from TK, from Google. Earlier, I mentioned the work from MIT and Stanford on compositional explanation. That's basically, those techniques will be useful because they on one dimensions from the work from Google, on they extract some parts of the pictures, and it's labeled, so they can capture the concept, and you can start combining the concept together. So you won't have the level of a dog with all the parts that they have, but you would have some level of representation, and it's captured again in the data that you have been labeled. And the work from MIT and Stanford, it goes in that direction, because the data they use is used for solving a segmentation task. So segmentation task mean a pixel and annotations. That mean an image, dozen and dozen of descriptions. And that's where you can say, okay, you can say that's a dog and that's a person, but you can also say that's a nose and that's an eye and that's a tail and that's pose and so on. So if you and then if you have that level of segmentation and then you use those techniques, then you can learn which neurons might be responsible for which descriptions, and start composing. And then when you do the inference, and this is what they did, the computer interpretation of neurons, you can start saying, okay, this is a dog because, and then you mentioned those part of the activation. So I really will go just a few slides back. The work I mentioned from MIT is called compositional explanations, and the work from Google on CAV and TCAV. There are techniques. I'll go. So there have been some work on this. And I'll go further on that, because in the next I'll go on knowledge graph, and I think there's a nice connection between machine learning and graph. So when you mention, well, how far we are in terms of describing, explaining this is a dog because of all the parts, usually the part, ideally you should have it in the segmentation task, and then but that's a lot of annotation. So what if you can get it from DBpedia, ConceptNet, or much more graph that describe connections between entities? I'll describe that later, so stay here. Okay, another question from LG. So when machine learning engineers use explainable AI and find that the wrong features are given high performance scores, what do they do with that information? So well, it depends. So if the prediction, or if the prediction is right, so if there's a high level of accuracy and the features is wrong, is there might be a correlation between that features and something that has not been captured. So let's say you want, I don't know, you want to predict the gender of the, or the ethnicity of a person, and you have a column that capture the zip code, and for whatever reason, and that has been shown to be true, zip code in the US is highly correlated with some ethnicity up to a level of accuracy, and you say, well, that's wrong, and so in that case, they should be removed, that features, because you don't want to have this correlation. But what's also happening is, even if you remove that zip code, there's other factors that you may not want to be finding. So they might find correlation, I don't know, between job descriptions and, well, whatever other features, and you might think it's wrong. And when you think it's wrong, well, remove that features and try to see what you get. And and again, when I say it depends, because it depends on what you mean by wrong. Is it because you get a wrong prediction, or is it because you think it's wrong? So it's but I suggest you remove it because you think it's wrong, and you go after other data, and you try to solve that problem because you didn't want to be happening. And maybe when you say it's wrong, is because you get very bad results. So if you get very very bad result with that feature, and it's at the highest importance, so that's you need to collect more data and different features. That's just the model is just completely biased toward this particular feature. Okay, thank you, Jay. So I have another question. How does the data affect the explanation? So well, it does affect a lot. Well, yeah. So depending on the amount and the quality of the data that you have, if and by data I really mean if it's fully supervised, if you have input and if you have output, and if the data is noisy, you get a model which is as bad as the data that you have. So, and the explanation will be maybe doubtful, or you might be doubting about the explanation, but that's basically because of the data that you have. So usually the explanation is a good signals of what the data, or what we learn from the correlation. And I think that's why people are using it a lot for debugging models. So I mentioned a paper that described who are the users and who is using it, and it's being used a lot for debugging models. And by debugging models is really, well, looking at the issues we have with the data. So so the data do affect those data, those affect those have an impact on an explanation, but you can use this explanation to fix your data, or to collect much more diversity. So I think that's important factor to be considering. So that was the question from Karim. Okay, so I don't think I missed any. Just doing a quick check. And thank you for the question. I mean, that shows I'm not. That's the issue with being virtual. So I know it has been more than a year now, but it's always appreciated to get some comments or questions. So thank you for everyone. So I'll move to the next section. So yeah, so less than 90 minutes to go. Okay, so I think we touched base on. So it has been a questions from Path on the, well, basically on the structure of the object that you detect. Can you use some part of it? So the sum of the work that well, I'm not the only one, but I'm advocating a lot. It's on the use of structured information for machine learning and for providing explanation. So then how you can use structured information in a way that helping you structure the discourse of your explanation. And so I have a few examples. So before I move to a bit deep in the approach, just a few elements. So because I'm advocating for a knowledge graph to be used in the context of explainable machine learning. Okay, I think I fixed the problem. So the recording is back again. So let me share my screen. Okay. Okay, so we can get started. So hopefully you get some time to refresh a bit. So sorry, just double checking the video. Okay. Okay, so where we stop, we stop. I wanted to move on the topic of explainable AI on using knowledge graph for machine learning. So so give a bit of basic on knowledge graph. So knowledge graph is basically a set of triples. You have plenty of examples. If you know Wikipedia, there's a DB version called DBpedia, and it's connecting pages and facts and name entities together in a nice way as a graph, and you can use it. But they're much more other sophisticated graph, and much bigger. So Wikidata is an example. There is ConceptNet, which is so pretty large. I think that the bigger they are, the more messy they are, but they're kind of useful, providing some structures and connections, and maybe synonymy, antonymy, word presentations between entities. But it's something which is available. It's there. It's for free for us to use. So and that's the point. They are graph. What kind of knowledge they bring and what can you do with it? It's to be careful, but it's definitely of use. And here I want to show you that it's definitely of use, and that we have been using it, and other folks have been using it for solving tasks on related to machine learning and explainable AI. So, well, in terms of graph still, so you may have many different techniques for building those graphs. They might be manual, automated. So you have different coverage. Well, as you mentioned, as I mentioned earlier, it might be messy, and when I mean messy, I mean it's not complete. It's plenty of human inconsistencies. People could have well, many relationship with some kind of object which doesn't make that sense, but it's kind of the beauty of the graph. It's connecting, and then you can do machine learning on top. So so what we I mean what we try to push is we try to say, okay, here is it's an image segmentation task, and rather than only using labels which use from WordNet usually. I mean, if you ImageNet, the labels are used from WordNet, so there's a few connections, but it's not that deep, that deep graph. But what if you now, instead of using labels there, you use labels from a knowledge graph? So that means here in the pictures, when you have trains and wagons and tunnels, they're not only, well, texts dissociated from each other, they kind of concepts which are linked in a knowledge graph sense, that they kind of make sense to be connected. So they have relations, and that's the thing. So they have relations, and that's the new thing that you add, is they have relations. So, and the question is, can we augment the input that we have with more semantics? So now, if you think about ImageNet or others or other data that you have, now just can we do something on top of the input image? So then, rather than having a label, it's a label, it's many labels with relationship that might be connected with other images, which were not naturally connected. So so maybe a train is connected to a tunnel, and then you have the picture of plenty of cars connected to the tunnel, and then while now the relationship could be made because you have much more relationship between object and concept. So you have concept of windows and maybe concept of speed that they're operating on the ground, and that's only on the surface, right? You can go even deeper and deeper and try to find connections between the two. So now what if, instead of having only pure labels, the classification result that you do, the class, it's much more descriptive, it's much more larger, it's kind of a graph that you learn as the outputs, and that might be something you learn to classify the input, but the input is an image described as a graph, and maybe the output is not only a label anymore, maybe it's a graph, and maybe it's this interconnection between those entities. So then now when you classify as a car or as a train, there's relationship between the two, and that means when units are activated similarly because they see windows, when they see a car and train, it does make sense to use those units for those different classes. And then you can start articulating and understanding a bit more connection between the different entities. The same, you can augment, well, I mentioned the input and the output. So here, it's a decision tree, it's huge, it's large, it's too large to be interpreted. What if you can summarize it and maybe provide much more semantic representations in the graph? And again, that graph structure, you may ask, okay, what does it really bring? Well, it brings you relationship, maybe a way to reconnect output. So maybe you end up in diagnosis particular disease, which are the same family, and that the same family, it's maybe you want to regroup all of them, and maybe all the properties you see on the decision branches, they should be all combined, and then you shrink the decision. And you may say, well, okay, but that's just a hierarchy of things. But now think about if you have a relationship, so that's, you can make even more complex and a bit more fancy in the way that you regroup maybe classes with similar relations, or maybe entities with similar relations might be grouped together, and maybe properties, all the properties of the features, if you articulate them in a much more semantic representation or graph way, then you can start recombining and playing with the causal structure of what a graph has to offer. And then similarly, instead of, I mentioned the work from MIT, from Stanford, from Google on the concept extraction. So either at the input level or either at the neural net level. But what if now, instead of having label, it's not label, it's entities in a graph, or it's maybe triples. So triples is a subject, object, predicate, object. So that's they kind of have a proper semantics. So so the work I mentioned from MIT and Stanford are using conjunctions and disjunctions. They don't go at the level of relationship, and the level of expressivity is still limited. It's pretty impressive though, but it's you can go further than that. So that's a recommendation or a suggestion. So, and here, yeah, that's the work I just mentioned. So what now if you do have graph representations on top of units. So here is the paper I mentioned, which has been published a year ago, and take a neural net architecture. So the examples are ResNet 18, AlexNet, ResNet 50, DeskNet 161. And I think it's probably layer 4 over here. And you have the unit ID and which concept or which conjunctions or negations or disjunction of concept are or compositional expressions is captured. And interestingly, they can say that based on the description, that they end up in a particular outcome. But then if they start manipulating the image, some of the neurons won't be activated anymore, which cause a different result. So that's kind of demonstrate that some of the neurons do capture some inner semantics, or that we could add labels or compositional expression on top of it. So they do it at the, again, they use the semantic segmentations, but they don't link it to a graph. What if you use a graph for starting structuring and maybe combining it even further? So that's a core question. And yeah, so use as input, so you can augment the input. So here it just some thought about augmenting a neural net input, output, the inner process, the labeling of the different neurons and layers. That's something you can add. And you can also, I mentioned it a lot, it's on the customization of the explanation. And I think that has been a question earlier. If there are multiple explanations, what do you provide? And I think it's definitely customizable, and you should definitely customize the explanation because it's really based on who needs what kind of level of explanation. And if I'm an expert, I might need to use description too here because I need to know what are the train characteristics. But if I'm a user which have no idea about what the trains types are, I just need a simple description of what the image is, and that's good enough. So again, that's something to be considered. And depending on the level of the analysis that you're doing, you might need some particular explanation for that, and need to customize the explanation. They also work on, so if you're in machine learning, there's some, you probably, and usually we do recommend using transfer learning for transfer learning or model adaptation or fine-tuning what you already have. And there have been some work that try to explain when transfer learning is a good way to be used. So based on the difference between the input that you get based on the targeted model that you want and the class that you will reach, there are some works on trying to explain transfer learning and when it is appropriate to work. Also in the concept of concept drift in machine learning, so that's usually applied in the context of streaming data. So when the data is changing, is updating on with a very high throughput. But sometimes the concept that you capture or the behavior of a human is changing, so it is not interesting anymore in some of the topics. So the initial concept that you were capturing is drifting. So and the drifting also could be on the input data, but could be at both. So then how you explain when you detect that drift, can you explaining it? So there have been some work also on this particular kind of work. And here I mentioned them, it's because they use graphs. So this work and the work before, they have input data, and they always try to augment the data with some kind of SPO, triple-like mindset, and try to provide explanation which is which has some rationale. So that means that there are some avenues for this. And so if we just look at an example, so that's something also I wanted to show, that if we don't use knowledge graph, but if we just do explainable machine learning, what's happening if you state of the art. So it's a boulder on a track. You try to detect it. You do not change, and again, that's not recommended, but just to be brutal, you use an existing image classification object detection task, well a VGG1, for instance. You do the object detections, and this is what you get. Well, if you filter on the top one object detected, this is exactly what you get. You can try it. I can try on VGG16 here, and this is what you get. But actually, if you reduce the threshold, so you have a threshold for the accuracy dimension. Actually, there is well way and boulder. It's there, but it's, if I will have added all of them, where many are wrong, you have 50 labels and 50 things annotated over here. And that's there, but it is not, because of you see the threshold is you need to put it down. So you can say, well, yeah, but just reduce it to 9%, and that will do the job. But no, because there will be plenty of noise. So the question is, well, how can I well, first get the right explanation and the right prediction? So if you apply state-of-the-art techniques, you get the object detected, it's a lumber mill, and you get this lumber and the thing on the right, which does make sense, right? After analyzing it, there's a lumber, so it sounds about right. But that's no use for human, because it's getting the wrong object. The explanation, okay, so it's 7C map like, but it doesn't really bring much. Well, maybe say that's a damage well track. It does convey this. And then if you do human reasoning, you check lumber mills, as I mentioned. It's a set of lumbers. Mill is a facility where you have logs, so you have logs over here. So it does make sense. So that means if you just step back, you just say, oh, okay, all right. So they connect lumber mill, they connect logs, and all of those things, they connected already in DBpedia. They already defined. So what's it's really missing? It's really the concepts. And then if you say, let's do the same exercise, you look at boulder, and it's very programmatically, right? So you just from a pragmatic perspective, just look at those concepts, and then you start seeing that boulder and rail transport are connected, that boulder are causing X percentage of accidents globally. So you start things connected, and then you say, well, maybe that's something you can use for driving the object detection to be slightly better, or to be much better. So that's what we try to do. So rather than having what you see on the left hand side, you want to get what you see on the right hand side. So you want to get the right object detected, you want to get higher scores, and you get an explanations that connect all of those entities. And all of those entities, it's basically using co-occurrence in the DBpedia pages. You capture the entities, capture the relationship, and try to see if they do occur together. And if in this particular image they do occur as object, maybe they are relationship, and what might be those relationship. And maybe if you look at the DBpedia, they will figure out the kind of relationship that we used to have. So obviously you could say, what if I would have changed the content and change completely misleading relations? Yeah, that's who you will have get misleading explanations, and that go back to the initial point that if your data is wrong or is manipulated, that make the explanation wrong or also manipulated. But that will give you some information, because here in this case, if the explanation would be or it's a boulder because it's connected to an airport, or whatever is the completely weird explanation you get. If you get that, you may say, well, there's something wrong in the data here, and the data is definitely from the DBpedia pages and the occurrence that you get. So if you get wrong data, you get wrong explanation. If you get wrong explanation, that means you need to fix your data. So that's the usual way you can do it. And fixing the data, it's not fixing it to fake it. It's to fix it to fake any bias that we have, to mitigate any missing data that we have, anything that's wrong. So, and if you say, well, maybe that's true, but maybe it's not capturing the transportation context, and you get relation which is true in other contexts, but not in the transportation context. Again, that's again based on the data. Maybe you need to refine the data that you have, and maybe the generic or the general purpose data that you use, that's not what you should be using. Sometimes it's of use, but sometimes you might need to refine it somehow. Okay, and this is yeah. So this is what you get as outcome. Object detected, threshold much higher, elements in the graph connected. Okay, a few references on it if you're interested in terms of, well, how you get the graph, how you clean it, and how you connect it to the neural net. The nice thing is they know retraining retry. There's no fine-tuning retry. It just say the model is as good or as bad as it is. Let's try to we use the external knowledge that we have to try to fix it. Okay, so we move to the coding part. So that's where I'll move to change screen, or at least use yeah, the code over here. But I'll pause here if you have questions. So here again, I'll pause 20 seconds. So again, if you see my pictures, let me check the link. I'll post the link again in case people join after that. Here again. Okay. So here it's that's not the code. That's where so the code is in the key. So I'll pause 20 seconds if you have questions. Here you have the different code. So again, apologize if you don't have a Google account, you will need one to connect, and that's because they use the GPUs that the Koller is providing. So strongly encouraging. I think you can still read it, but you won't be able to execute it. So okay, so let's get started. So I look up at the slide again. Okay, so first is Lime. It's getting older now. So it's 6 years old, but it's the baseline. Is really it's one of the techniques you should. Well, it's still there. It's still be used by well, really as a baseline. So I think you should. That's one of the ones that you should know. So so that's why it's there. So here I just copy some content from Christian Artiga. So it's pretty good collab that they did. So here what you see is left hand side a picture of a dog and a cat, and Lime it just capturing well, patches of what's making the explanation there to be captured as a lab writer. So it's captured as a lab writer. There's a few video explaining. So here I won't go cells by cells because I think I have 12, 15. I mean, yeah, 2, 4, 6. There are 14 techniques. So that's maybe too much to go through, but I won't go cell by cell. I've been pre-executed first, but you can use it for Oh, thank you, Jay, for sharing that. I thought I did. Yeah. Okay, thank you for that. So yeah, so they're here to be used. So feel free to make use of it. So yeah, so Lime, yeah, so that's based on Keras. You have the input picture. You can use whatever you need. There's no rocket science over here. You use Inception v3 as the model, so you can use whatever model you want. Okay, so here's a set of explanations. There's a step that kind of divide the different part of the picture. So it's a segmentation task. So, but it's done kind of well random base. So if you run it differently, you get different segments. So you get different explanations. So that's an hyperparameters that need to be changed. There's a number of perturbations that you're doing just to see what kind of combination I'm removing, just to testing it. Here is an example of the picture where you remove and then you analyze the predictions, and then you do the prediction. You get the different classes and the different scores, I think here. And then, yeah, and then, so that because you do different well, combinations, at the end, you pick the one that well, minimize the loss of accuracy at the end. So that's one technique. The second one, and again in the slide, you can click on the link, it goes straight to the collab. So that's make things easier maybe. Another one is on Lucid. So I mentioned it earlier. So Lucid is in here. So it's a pretty neat. Oh yeah, so random patches. So yeah, so use this segmentation over here. Well, it's not random in terms of numbers. I think they mentioned 200 if I remember. Where is it? Oh, here. Yeah, so the kernel size ratio, maximum. So there's a few parameters that you define over here. So while it's not fully random, it's you define some properties of it. So you can see and change it. You'll get different patches. You can reduce. So yeah, so you can play with it. So well, I think the smaller the better, but the smaller they are, the more combination you need to compute, and the more time you will need. So, but so there's always a trade-off, right? So because you need to find the right combination here. So thank you, Paul, for the question. So yeah, on Lucid, so it's visualization of neuron. So here, so we use the mix 4A. So it's the one before you do the real nonlinear activation. It's layer number 4, and the model it uses, it's Inception V1. You can try many. So if you can try many other models over here. They imported from models as models. So yeah. Then there's a model zoo in Lucid. So there's quite a few number of models that you can be using. But here it's Inception V1, and here they basically visualize one of the neuron. This is 465, and they have different rendering visualization. So here, I wanted to show that you can visualize in different way. So you can use based on so here you change. Okay, here you see different another one, and here you combine two channels. Here, so you can even combine units together. And here they have a transformation. So they use it's an MC transformation, but you can use much more complex transformation. And based on the transformation, again, we're always on the same, right? So it's always the same unit here. You can see you get this visualization, and then here you get this one, which is a bit more crisper, or it's different. it's because you use different transformation mechanism. And here you have even much more transformation, much more complex. And you can see this, well, you can add many, right? So change the scale, the padding, and here you get against something different. And here I wanted to show that it's because the visualization is very conditional to the transformation that you do, and usually it's really, I won't say it's cherry picking, but it's you need to try different things to get the right visualization. Usually you get on average pretty good visualization, but if you want to get something more convincing, some are more than convincing than others. But some are, so here you see this one is capturing nicely bubble like shape, and then they use different parameters. So yeah, just here to give you an idea. So you pick your favorite one, your favorite architectures, try those transformations, try different neurons, try microscope, which I strongly recommend to play with, because it's already pre-computed, so you don't need to compute it again. Oops. Okay. Can we move to another one, which is on XAI concept on image? So it's concept based. It's the work from Google I mentioned earlier. So that's where here where you have the class zebra, and you capture different texture. So you can see that here the texture of type striped is kind of representative of zebra, and this is what we mean here by concept. So, and here the concept is you have a texture, and the texture, and that's because they use a particular data sets which have many texture, night and stripped and bubbly, and they have many of them. And the explanation is those concepts that have been representative for this particular class, and they say, okay, that's a zebra because it's stripped, or that's sparkling water because it's bubbly. That's what kind of things that you could do. So if I look in here, yeah. Okay, so it's part of a deal consortium in Canada and Quebec that they deploy a new library called Explic. There's many, you'll see at the end. I'll show the list of libraries. There are many, and this one is a new one. So Explic, it means explain in French. And they embedded, or they incorporated many techniques, existing techniques for explanation. Yeah, lots of different techniques of explanations, and that's pretty good because it's all they're using the same interface, so that's pretty neat. And in addition, they provide many evaluation metrics. So here, yeah, so they use the texture folder. So this texture, this is what I mentioned, the strip part, the bubbly part, and they use the data over here. And yeah, that gives you example of texture that you have. So if you want to explain why you get a concept, they will try to connect what kind of texture it's used, and you see it's quite large number of texture. Well, so you have night, white stripped and bubbly, and we can see others. And here you have the different pictures that we show extracting from the data, and they use CAF. So this is the Google work I mentioned earlier, concept activation vector. There's also the TCAF work, which have been done, and they basically we use it, and they have this interface Explic, which capture the concept. So, and you have many others. So earlier I mentioned the Facebook Captum. You also have the Explic one now, which with other techniques. Much more attribution based though. Yeah, and then you see the feature visualization. So you see the features, you can see and visualize it in the lucid way. And then now when you test it, it say, okay, the class zebra and the class tiger, and the final result, yeah, and they show based on the class that you have, what kind of texture have been used, and that texture, it's their concept. So please use it. It's I mean, there's many more at the very beginning here. You have much more way of tools. So here it's TCAP that's used, but you can extract others, and they really activation-based techniques, gradient-based techniques, attribution-based technique. Okay, so we move to the next one. So GAN, so that's the work from MIT I mentioned earlier. It's on, well, it's for GAN dissection, but you can use it for CNN. And it shows, so here so the one that's used here is, what's the name over here? It's the ProGAN, yeah, that's the ProGAN architecture here. Okay, so you see the model. Okay, so you can run a model, you can do some inference, and you can visualize the output. So again, it's a min-max neural net. So the discriminator generator, and we really try to generate new images, and they try to see on that network which neurons is capturing what kind of labels. And you see the GANs are generating pretty good images. So there are examples of images that they could generate. And yeah, and here it showed the image activation that you have here for a particular class, and based on the different units, which concept I think they show the importance of which part of the image is, and most importantly. That was the end. Yeah, over here, you see the different classes. So they mainly say so for each unit we print the unit max for the top activated images, and that's something for a particular concept. So trees should be somewhere over here. It should be described earlier at some point, but they describe the different trees, and they mention where it is, and it's which neurons is capturing. So 42, 44, 9, and so on. So the neurons capturing the trees. Yeah, that's semantic segmentation here. And same exercise over here, but much more. I think it's on sky and ground. So I think that towards the end, it's more. Yeah, so that's the trees. Yeah, so that's the index tree. So that's the tree that you're looking for, and they try to see which units to unit 365, 157. So and with the unit and the IOE score, and they show the unit visualizations based on the image that they have. So that's the different images actually, and they see the different units and how they react to those. And that basically going back to the concept that you have a unit, and the unit is capturing a particular concept. So here a tree, and you see for each image the trees it's indeed captured by this particular unit. And if you take another unit, you try the same thing, you won't get tree, because the goal of that unit might not be to capturing trees. Okay, so next, and I'm sorry again, I'm going pretty quick because there is 10, well, 12 different techniques, and the code is there. You just need to execute it, read lines. Happy to answer any questions if you think if you may have, but that should be self-explanatory. And then we're moving to some of the work which has been presented at NeurIPS last year, which basically try different techniques on different data. So they try text, they try images, and they try time series, and they apply different techniques of explanations. So that's where we're going to go now. So that's the next one. Again, this is the different link to the different collabs. Okay, so that's so here there's slightly few more things to do. So you need to make sure you connect it to your drive, but this is here, and you need to push some elements in your drive, some image, push some data, I think. Yeah. So this is why you need to push the examples, and you need to have that. But then after you did those, you go to the drive, you get it, you push it on your drive, you put it in these exact locations. That should easily run with no worries. So here it's based on example based. So you take, so we already have the train and the testing data sets. So you load the model. Okay, so this is why the model is loaded. So the architectures used, which one is it? It's okay. It's not well, it's not mentioned. It's a pre-trained model that have been used, but it's not a super complex model over here. But yeah, the model is pre-trained, so you can't really train your own architectures over here. But you that's the one that it's used. Yeah, but you can see it's a few set of convolution, so it's not a big network here. And you choose the, okay, so here's the well, it's not the tricky part, but it's the because when you see from the outside, you say, okay, that's neural architectures. They find examples which are similar, but then how they do it? You can do many different ways. You can only use the data and do comparison. It has been shown that only comparing the inputs doesn't work. So you need to have the right level of representation. And by the right level of representation, I mean, you need to get in the right output of a particular layer. And that particular layer here is flatten one. And flatten one, you see, is just before the dense one and the output. So just right after the last convolution network. And that's the way you have a 300 dimensions, and then you reduce to 20, and then you reduce to 1. So that's where you have 300, and it's quite representative for doing comparison. So you basically take your input, you're going through all the neural network up to the ConvNet number 3, and then you have a flattened one that flatten the 12 times 15 that give you the 300, and that's where you say, that's my representation of my image, which one is the closest in the space? And that's basically how you do example-based comparisons. That's not more complex than that. You can try you can try different layers and flatten at different maybe at that level here. So 256 times 20, and you can try, but you will see that it's not as convincing results. And that's results. Well, globally, I've been showing that that layer just before right after the last convolution is the one that worked the best. Okay, so and then here is the example. So it's text-based. So you can see there's a review, and then you want to find similar examples. And similar example is based on the neural. So I'll let you read it and judge. So again, the neural net is not the architecture is not so huge. The data is not so big. So it's interesting to see what you get. But that gives you a sense of what is it. So if we still use the same work, but now instead of using text, we use images. So while that's the same setup, but you have only 10 classes. You have different models, obviously. So the architecture is slightly different. It's a bit bigger. So CNN based, that's convolution network. And again, you see here, you will do on the flatten one. Yeah, you do the selected layer on the flatten one. So here, the difference is after there's a few other things. Because you do classification on 10 classes, so there's a logit one, probability, and so there's softmax, and so that's so they slightly more, but this is where you have your representation, and then you can use there's a few adjustments for coloring, adjusting images. You just can take the code as it is, and then this is what you get. So you get the input images, so that's the track, and they give you 2 examples. So you get the 3 examples. The same for birds. They give you the closest examples: automobile, frog, and again frog. Yeah. So that's so you can see that, well, some are questionable, right? The last one on the truck, it's not a really similar example. Okay, so let's move to ECG. So ECG is just an example of time series, because you may want to do explanation not only on images, not only on text, but also on time series data. And just to show you what's time series. So time series, so it's ECG, so that fusion bits. So yeah, so that's what it's normalized over here, but it's give you a normalized bits over time. And the example of explanation here, it's example based. So it's example based. So and just here to show. Yeah, so I'm sorry, I've been too quick. Yeah. Same setup initially. So it's a classification task. So you have a pulsion site and you try to make classification. You have the model. That's the architecture. You used, it's slightly more complex than the text one, but well, similar spirit than the one for the image, and then you use example based. So so you do yeah, and that's so use the flattened one here, and the example is the fusion bits, and they give you example of it. So it's basically example based. So this is what you see here. This is the example that you want. So and again, is doing the same based on example. So it shows that and again, you may question, well, is that really an explanation? It doesn't really explain the temporal relationship. So if you want to explain why are you dropping here, that doesn't help. What does help is just say other people with the same behavior also drop, and maybe you should look at those particular data points and or maybe features associated to the particular person, but itself doesn't help. So that's why I say example is good, but it's you need more. You definitely need more. So if you want this to be used, you definitely need more. Okay, I'll move to the one on graphs. So that's the one where I've been using Captain, so the Facebook the Facebook one. So so this is the Captain library that you use. So it's we use Torch library here. You need to test or to get the data. Multi agenicity is a pretty well known and well used data set. So it's a graph about and the goal is to predict if you have if you can mutate in different groups. So that's what's the goal. So so this is an example of the graph structure here, and because that's a graph, you build a model based on the graph. So it's a graph neural network. They use graph-conv, which was edge weight as parameter. So and be careful because there's many hyperparameters that you can tune. This is the architecture which has been used. You can change it, but it's pretty simple. A number of epochs because you need to train on the data. You see that the loss is decreasing. Accuracy is decent somehow. Pass on the details here. And then and this is the input picture. And then when you do you have your graph neural network, you do the training, and then because it's a neural net at the end, you can use any library that can consume that neural network for computing gradient backpropagations and evaluate importance. And that's where you can simply use integrated gradient here, which is used from the captain, but you can also use saliency. So that's very convenient. So well, the most complex part is you design it as a graph, you get the right architectures to get good results, and then you just apply that, and then the explanation for this to be well to provide mutations, to give mutations, is to have those particular molecules over here. So that's what made this particular molecule multi that could mutate easily because they have those particular molecules. So that's pretty. You can apply to your graph and you can try it. So it's something I liked a lot. So, and if you look at the slides I presented on a graph neural network and explanation, you have counterfactual based explanation. That's something I wanted to integrate as code, but you can go and check it out. The code. It's also pretty nice. It's pretty neat. So it's another piece of work that provides explanation straight out of a graph neural network. So you have a graph, then you can learn a model based on the graph structure, and then you can apply classic neural net architectures. So very, very nice work. I'd strongly encourage if you have graph structure. So all of those techniques here that you see, they can be used. So we use integrated gradient and saliency, but you can use others. Explanation comparison. So I think that was a question we had earlier. So again, thank you for asking the question. So that means now that you may have multiple explanations, you can start comparing. And then if you do deal with well, stakeholders with no experience or in tech or in machine learning, then you can say, okay, here is what I get. What is the most compelling for you? So I'll set up as initial, and I'll go straight to, because of the same data, they just show examples. So yeah, so on the confusion matrix. But what you see here is we use which one is it? What segmentation? Oh, that's Lime. So it's Lime applying here. So this is what is detected to be a truck, and then the next is a cat. And interestingly, you see that that's not a cat. And actually, we see what is focusing on. I don't know if, I mean, it's quite difficult even for human to look, but it might sound like it's detecting some kind of hairs here. And it may think it's a cat, but it's wrong here. This is why it's representative as for a car, and this is what is representative for frog, and again here for frog again. So that's using Lime. So here you can show to the users, okay, you have images, here you are, does that make any sense? And then you can use anchor explanation. Anchor is another technique, which is Lime on steroid, basically, and that show the different results. Right here, prediction wrong, but the explanation is slightly different. Here it's slightly more focused, and here even more, and here is off. And then you can use Sharp, and Shapley it shows the rather than defining an area, it just shows kind of heat map like on the truck, on the cat part. So cat for me is completely off. So, and that's interesting because you see the explanation is off. So even if you don't look at the label, you may say, well, I'm not so sure that that's the right. So I'm not convinced that that's the right. So then you might start questioning the data, and the data here is the picture, is the image, and the label, and that's the label is the prediction, which is cat. So that means you get a good guess that the explanation is helping debugging your model. And saliency maps, GradCam Plus, so much more heat map like, because the areas are much smaller over here, but it shows the different areas here. So you get a sense of what's what people are doing in the explanation field, right? So they show examples, they show superpixels, they show areas in terms of text. They show example of text, attentions. They may link entities together. So that's a few examples over here. And yeah, that's the examples here. So for truck, and you see for cat. Interestingly, this one, if you look at the latent space, the cats were the most were close by. So that definitely means that, well, using superpixel you get cat. Using well, you don't get cat, you get stuff off. But here at least it shows you that, okay, it shows that the base, well, when they did the discriminations, or when they try to find a good representation of for this picture, they cluster it in where you have plenty of cats. And most likely this image here, you don't have many of them. So that means it's just one in the middle of many cats, which actually when you see, if you see that, that means I have something wrong with my data. So this kind of example-based explanation helps in debugging. Frog and frog. Okay, and I think that's nice. The last one on codes. So that's some code I've went through recently, and I've seen pretty good work on exposing metrics evaluation. So this is very nice work. So it's called Quantus. Provide the details over here. But they go beyond only providing new techniques or techniques. What they do is they provide so here what they use NIST, so it's very simple, but so they train the model. It's easy to train. They generate explanation. Again, that's not where the explanation they do use existing work. So the one from Quantus, the one from Captain Facebook, the one from Explic, they use existing ones. They bundle it, interface it. But the nice thing with those last one I show you, is they provide the evaluation metrics, and that's where I think the gold here in those two, because people they play, but they say, well, now how do I evaluate it? And you have many ways of evaluation. So you can define the parameters for the evaluation. So the similarity function. So there are many ways of making the similarity and comparing it. And here they show, and then you can start comparing and say, okay, I have the salency scores is this 167 and the integral gradient is 0.76. I know it's only figures and doesn't resonate, but you can start comparing, because now they have the metric and they can compare salency-based techniques, integrated gradient, and they show that you can start comparing and show the different results. So that's something I strongly encourage. If you could look at the techniques, if you come up with your new techniques, do evaluate and do benchmark against existing techniques. And that's what I want to show you is the deep explic. Again, not on the new techniques, but much more on the evaluation that they have. So here the different explainers that they have. So salency, gradient inputs, that's something we covered. Guidance, they all integrated gradient based, so attribution based. So here they all attribution based. So you see all the one we quickly touch base, GradCam, Lime, Smooth Grad, they're here, and then you can see the results. So here it's only qualitative evaluation based on the salency. So you see different picture, but you can see what's the different result that you get based on which technique that you use, and you can see a different superpixel representation and compare, but qualitatively. And I think that's pretty neat. And then you do have those metrics, and I think that's pretty good. You do have metrics. Well, you have deletion metrics and you have scores. So you can say, okay, use all of those techniques. What's the score using the deletion matrix? And deletion matrix is one of the metrics that people use. And then you can compare those and see. So doing deletion, there's insertion techniques for evaluation, and new fidelity, and the stability metric. So there's much more than that. So you can go much deeper, and I think that's something that was missing probably a year ago. I mean, when I discussed this topic a year ago, we didn't get that many evaluations. So something good is now we do have metrics available. You need to find the right. It's always the challenge of finding what's the right metric fitting to the right objective I need to get. But now we have more and more metrics, and there's probably one or a combination of them that could be used. The same for explanation. Now there's one, but even if they can use different techniques, example and concept based, you can still now even combine the two, or even combine sub part of saliency based techniques, and it could be a mismatch of many different things, and then evaluate based on those techniques. So I strongly recommend looking at this. So I think that's it for the code I wanted to share. So I'll pause 20 seconds. We do have 15 minutes, so I'll probably slightly go over. I know it might be super late for some of you guys. But if you want, you can stop. Again, I'll share the recording later on tonight. As soon as it's done, push it on YouTube, push the link on the link, and you can go for the presentation again. I'll pause it again if there's any question, and I'll move to the much more applications. But I'll go pretty quickly over here. So I'll just pause 20 seconds. Okay, so you can still use the chat if you have questions, but in terms of applications, you see many. My company has many applications because we're dealing with critical systems. So here it's so we're dealing with trains that need to be autonomous, and submarines that need not to make the wrong move. So they have models that detect objects, obstacles, and they need to have the right justification. And the example of justification here is one of the techniques I show you. So you detect obstacle, or you detect an object, and some are not detected because the threshold is too low. So how you make that happening? So basically so here initially you don't have the information about the paddle, so you don't say so if you use classic techniques, you get paddle 50%, person 60, man 46%. And on the right, so this is what you see on the right hand side, this is the end result. You get a person at 66, so the same, man 56, so slightly higher, both 58, which was not there initially, and that's a way where you use knowledge graph for object detection here. Try to find co-occurrence of terms in a graph, and does that make sense in a picture? Do you capture those? If they are, most likely they may be connected, right? So and the score should be much higher. So rather than having a boat which was less than 10%, because you don't see the boat much, right? So now you say it, but the confidence was pretty low. So now you make it even bigger. We also define there are a few links here. I won't go on the link. You can go for it. If you don't have access, I'll grant you access as soon as I get access to my email. But it's a video showing how you can combine the different explanations. So a person asked earlier, is it what's the right explanation? But actually you should combine them, and maybe you can try and compare. So we build a platform that get the data, get the model, and build different explanations, but much more visually. So now you don't need to put it in a Google Colab and try different things. Now it's really up and ready. We use counterfactual. We use gradient-based techniques. It's a combination example-based techniques. That's there, and that there's the video available. There's also some work, so that's also something I wanted to mention, because there's very nice startups working on the topic. So, well, Fiddlers.ai is one of the prominent ones in the field that have very neat work on the topic. So I strongly encourage looking at the platform that they have. We also working with a startup called Zetan, which look at the inside of the neural network, and they really try to understand the rationale and try to go deep on the explanation between in the neural network. So it's really focusing on neural network and visualization. Strongly encourage to looking at that in particular. So some work I mentioned earlier, object detection, so that has been covered. So the work we're doing with with our colleagues in Toronto for explaining obstacle detections. We're also working with some with the airline industries and try to make explaining. So when a plane is landing, there's a right level of inclinations. So you try to get that right level, and that's you try to predict what might be the right depending on the weather conditions, and you need to find the right explanation. So we provide tools for explaining why we end up with this particular decision, and that's a combination of features, and we use the platform I just described earlier. I also work with an airline company back when it was done in Accenture, where we try to predict flight delays and also explaining flight delays. And it was very critical for them, because explaining it will provide them insight of what needs to be changed, or maybe the strategy, because flight is not operating only one. Well, plane doesn't operate a flight a day. It does operate on a sequence or a chain. So if you do have the explanation of why a plane is late, you might be correcting for the next schedule accordingly, rather than just saying, well, I know it's late, but we have no idea. And actually it's a sequence of actions occurring over the set of flights, and they all require techniques for exposing explanations. And that's some work that we been published at AAAI 2 years ago. So some work on risk management and trying to predict if you say you get lengthy description of a project and deliverables and who is going to work on it and what is the industry, who is the client, what's the likelihood the project is going to fail and why. So at least you can mitigate risk. And it's nice because it's time series data, because you have data coming from day one, even day -1, because what was the requirements, what was the engagement, what was the IP policies, and so on, and up to the final delivery and the impact on clients and maybe the press release. So we use lots of heterogeneous data and try to understand if I get a new project now, or maybe during the course of its life, what might be happening, and why will I need to correct to make that happening. Some work also on travel expenses, so try to explain why employees are spending more than others in particular locations, particularly when they travel for conferences or for visiting clients. So we try to detect abnormal behavior. So not in the sense in trying to find why is that person claiming so much and maybe making a fraud. It's much more, well, the rationale maybe because the number of people going at that day, it's much higher than usually for that kind of size of city, that kind of set of geography. So, and that's actually a normal behavior. So, and for that we use a lot of data coming from external data. So DBpedia, we used a social event from Eventful, and was try to combine and make sense out of the contextual situation in a city. So then next, you're not flagging employees to make a fraud, but you have an explanation for the auditors to understand why it's abnormally high and that's not on purpose. On other work on counterfactual explanation, so that's some work that we presented at during the challenge for NeurIPS in 2018, where we try to do counterfactual explanation. So here is what you see: the different features describing describing the history of a person, and then you just decide if you accept to provide a credit applications approved or disapproved, and those features that you see on the left can be changed. So basically, you end up with a recommendation, and if that recommendation is wrong, counterfactual is really what can you change to make it right. And this is exactly what you see here. That means you see the set of features. And green means what you need to get, where you need to get higher, and red what you need to reduce. And the left panel, what you see is you have locked. So maybe there's some features you can change. So maybe in your application, there's something about the geography you live in, and maybe that's, I don't know, I just make it up, but maybe that's part of the model which is used for making the predictions, and maybe you can change it. So if you can change it, but then maybe you just log that features and say, okay, do me counterfactual explanation, but don't change that features. And then those won't change, and you only see the one that change over here. So it's a pretty good example of what's counterfactual and how it could be used for explanation. We use it for in the context of medical context. So try to diagnose disease time series, and try to find similar patients and try to see what kind of, but using graph. So what I show on the graph on the GNN, that was using exactly the same context. You have graph of patients and the time evolutions with connections, and you try to see what ending up to a particular diagnose given all the history of that patient, but also the connections of symptoms that that person has, and also the other patient, and you try to find the core edges, the core nodes that make that particular predictions. And here the predictions is you really try to, it's a link prediction task. So you predict a node or a node of a person to be linked to a class to be a particular disease. So you try to predict that, and you try to find the core subset of graph that are used here. Then there are work on explaining visual question answering. So then asking questions and which terms might be important in answering a question. So then you can find which term are of use. So then they identify which core elements in the question is important, and that's part of the explanation. So when they have the questions, they have the answers, they relate. And again, usually when you do visual question answering, you have different backbones. You have an image backbone, while you have a CNN backbone and a transformer backbone. And so the attentions, you need to attend the image on the question type. So you need to add a specific mechanism, and the explanation is this extra thing that you add. So again, neural network, if it's multimodal, that means there's multi sort of data that you're using. Attention is something you should be using if you want to make up connections. And usually when those make-up connections, there are those attentions, and those attentions, usually they could be used somewhere to provide explanations. I think the shortcut is a bit rough, but there's lots of work at addressing and studying this topic. And there's more work from LinkedIn on debugging and explaining relevance, or scoring for a particular job, who might be the best, and then trying to find why that particular person has been ranked first for this particular job. So especially for people that from human resources that looking for candidates, and they try to get a sense of why they get these results. So that's been embedded in the LinkedIn. And also even some work on trying to adding so I wanted to work done by Facebook on why using a particular post. So and you see this post, and they provide a rationale, which is well, you make a recommendation based on the feature. So and that recommendation is because of, and then they use the usual suspect techniques, right? Removing and say you get the same recommendation. So obviously, if you not have this connection with this friend, you will not have this. So so that kind of techniques to be using. Yeah, on the other techniques on sales predictions being used. So they provide the companies and try to predict on sales and find which features are the most important. So here they based on contributions, feature importance and line, talent search space, human resources, again, and some work on breast cancer survival rate predictions, and try to get a sense of what might be the explanations, and you get the textual representation and a bit more further analysis. So I think it's a nice way because it shows different pictures and different snapshot of what's an explanation look like. And you can go on and go on in terms of application as more and more energy consumptions. I mean, why do I have these particular patterns over here? And so you can use the example-based techniques, and you can see different examples, similar signals. That's an example, and then you can try to do a deep analysis on those examples. What do they have in common? Or you can also start connecting and saying, okay, I have a peak of energy consumptions, and the only thing I'm measuring is the energy consumption. That's it. So, but maybe there are events, or maybe there are weather conditions, and you're adding data, and then you try based on time series, we are correlating and find patterns and relationship between past events. So you can say if those events happen in the past on another stream of data, and then it is impacting at time t. So that's example of explanation that you get. Same again, energy consumption here. So I'm done on the application. So now we just slightly go down towards the end. So I might go 10 minutes over, but that would be no really deep technical content. It's just some notes that are available and I took, and that might be interesting for you to know, especially if you're entering the field, to see what should I look at. So I give you well, some papers to read, some conference to go, some tools to use, some codes to reuse and integrate in your code and make evaluations. So now there's plenty of new techniques that you and tool set that you have for you, but there's much more. So here's the set of tutorials and workshops. So if you do planning, machine learning, image classification, reinforcement learning, if you do imitation learning, there is a venue for you for doing explanations. There's many workshops. I mentioned workshop on explainable recommendations, visualization, neural network. There are one on purely on fairness. So really, depending on where you are, you should look at where the workshop at the core venues, NeurIPS, AAAI, ICML, ICCV, any usual suspect conferences. Look at the workshop, and you will see niche papers, which is sometimes pure gold that you can reuse. So I really strongly encouraging looking. So this, use it as kind of a map for you, just to go in the field of explainable AI and going in the right field and asking the questions. And here is the list of tools. I keep adding things on a timely basis to see any new work. So and there's many more coming up. So, and now I think having GitHub source code for having paper published is kind of a must nowadays, especially if you want it to be reproducible. So I think you'll see more and more tools, but here I list some of them from the top usual suspect, Google, Facebook, Amazon, IBM, and others, and the one we just described, the Quantus and Deal Explic, are tools that you should be considering for evaluating. But now a lot of tools have common interfaces for using most of the tools. So the higher you go on the list, the more integrated they are. And then in terms of initiatives, so if you just step back and say, okay, but who is doing really explainable AI? So in the US, DARPA initiative a few years back, very interesting result. They've been moved quite big on the field. They make the tempo pretty good. So a lot of papers, tools have been emerged since then. There's also work in Canada. So Deal, I mentioned the Explic. That's coming from the French dimension, but the Deal is expanding, is also in Canada, and there's also work and techniques there. So strongly encourage looking at what the consortiums are doing both in Canada and both in France. So they're also great resources to be considering here. There's the initiative in Europe. So the AI for You is one European project where there's interpretability in there. Another one called Confiance .ai, which is another consortium dealing with AI engineering, but also have issues related to machine learning ops and interpretability, explainability, and making AI and machine learning working in safety critical systems. So that means trust is at the middle, as the core of the mission. So again, Confiance.ai is something that you should be considering looking at. There are many more tools. And conclusion-wise, so if you just step back, so why do we need explainable AI, by the way? So think about users. The users, well, think about your applications. So what if you deploy something that is going to make mistakes? What's the impact? If the impact is measurable and it's critical, then you can think about explanation. And then when you think about explanation, you say, well, who are the users? Who are the regulators? Who are the person that make certifications? And connect with them and empower those users. That's the one that are the one making the final decisions. And if they decide to get the particular piece of model or software in a system that will be embedded in a critical systems, they're the one that put the stamps. So if they're not convinced that there's the right explanations, or the end users cannot make use of it and just say, I'm still using my initial techniques, that's not good. So start with the problem, with the application, with the data, but very, very important with the users. So it's important because it reveals and protect new vulnerabilities. So it's used to debug, to make the model better, to make the model scalable, to detect bias, discrimination, whatever metrics that you care, we will reveal important effects of what you're doing with your model. Because we need to implement the right of explanations. That's in core scope of GDPR in Europe. To improve industrial standards, I think standards have been a bit behind because of the AI wave. So they kind of try to figure out how they can adapt standards and how you can do it. Regulated cars is, that's the question, right? So people are still working on self-driving concepts and for the right reasons, right? But they might be reaching a point where those questions might be raising, and so something to be considered. So we also help people making better decisions, also biasing the model towards human values or towards company value, if that's that's ethical in terms of what should be the company should be doing. So think that explanation might be doing good in the sense that you can use it for manipulating the data and then the model, but you can also use it that give you way to attack the model. So that's something I haven't touched, because I think they have workshop and tutorials on model attacks, poisoning models. But I think explanations is also the side effect. You can use it for attacking, but also then for preventing, right? So and scale and industrialize AIs. That's also the important part. So explainable AI, so that's motivated by real-world applications. I don't think so. It may have come from a technical angle, but the business need is definitely there. You'll discuss with many. I'm discussing with many clients that asking me this to be embedded in these systems need to be trustable. That's very core. That's a must in many applications. So now we just need to reconnect the technology side and the business side. So we connect the two and making sure the user is pleased towards the end. So it's not a new problem. It's just a reformulation of past research challenges. It's multidisciplinary. I mentioned user interactions. I mentioned a few analyses. I mentioned a few studies where they analyze the users. What kind of profile? Is it much more for debugging? So they would analyze beyond the technology. What's the user needs? What's the how you do customized explanation? And in general, there's many complementary techniques. And I think I mentioned from the very beginning, explanation should be multimodal. It should be embracing many different techniques, and it should be it should not be one shot. It should be conversational, maybe, I don't know, maybe, or combination of using different medium. It's a mix, right? Models are getting much more multimodal, coming from data coming from images and sound and signals. It's very thing about MV3D architectures, which is a fusion model for self-driving cars. It's 3D object detections using lidars and using optical cameras. So it's coming from many different backbone, right? So you need to consider that. So there's many industrial applications there which are already there. So they definitely implemented, definitely deployed, definitely used. So definitely in use. There's no more question about it. We definitely there. We just need now to convey much more human-like explanation. So something that could be composed and much more easy to capture from a human perspective, much more for a lambda human, from a beta user with no technical background. And needed explainability by design, so when building the ag products. I'm mentioning with the life cycle, but that should be there from the very beginning. And there are open questions, so still people are not, there's no agreement for what's in explanations. They even use different terms. Sometimes they mean the same thing, but sometimes they don't. There's no really formalism. There's no one definition that say that's an explanation. And the reason why is because they're human behind, and that you're starting having philosophical questions about what the user needs, what's pleasing someone. It's a complex question. There's no work that seriously addresses the problem of quantifying the grade of comprehensibility of an explanation. The interpretation of an explanation is something which is open. It is still possible to join local explanation to build globally interpretable models, and open questions. What happens when black box make decisions in presence of latent features? That's also something need to be considered. If there's some bias somewhere, and then the model learn this bias and use this, well, then how you capture that, given that you don't have access to the model. So example-based might be some techniques that could help. What if there is a cost to query a black box? So So you may think about in the future that people charge for having an explanation. Can you monetize explanations? Is it something you can do? How to balance between explanations and model secrecy? And again, when you start providing explanations, if the explanation is kind of revealing the secret source of a knowledge of a model, you start having tensions now. So that's something to be considered. And future challenges, so creating awareness, success stories. I think we have many more. Foster multidisciplinary collaboration. We do have more and more. It's nice. Helping shaping industry standards. I think we're still behind, but even if we see some kind of ISO standards or coming up. Still unsure about where the explanation is really used. More work on transparent design. Investigate symbolic and sub-symbolic reasoning. Anything along the lines of neurosymbolic reasoning, it's pretty interesting result where explanation could have a huge impact. XAI is a methodology for debugging ML systems. I think we there already. And benchmark, I think we still need benchmarks. I don't know. We were asking the questions a few years back. Still don't get many because there is no really ground truth explanation. But if you provide ground truth explanation, you kind of by using the task of explanation, and it's yeah, we may end up in the problem of always solving a task for the data, but then the data is only one problem, right? The explanation problem that we have is for other kind of data. So even if you make it better for this piece of data, doesn't mean that you will generalize. So we end up in the machine learning trap here. So I'm not so sure. We need the benchmark, or we need way to better evaluate. XAI challenge, yeah, and human-based evaluation protocols. I think it's very important. So I think that's conclude the tutorial. So it has been 3 hours and 15 minutes with you. I do have more time, so you can ask me questions in the chat. So I'll let that slide open still, so you can email us. You can go to the site where the recording will be posted later on today. So feel free to check it out at that time, and you can say and send us email and ask us any question that you may have. So okay, so I'm starting to get questions. So thank you. Okay, thank you, Anting. So quick question: is there any interpretation algorithm for forecasting models where the importance of past time step points are highlighted? That's a pretty good question. So that's a very good question. So to be honest, I haven't seen it that work much. So where you try to, when you have the time series, you do predictions and they align the points in the past. They have seen some adaptations where they don't treat the time, they treat the time segment as a feature. So, time series is treated in a particular way. But here, what they treat is to treat the time series, the timestamp as just a particular features, and they try then to use existing techniques. So, and basically they say, so for them, it's the time series is multi-points, and they push it in the space, whatever the time. So just forget about the time, and they push it in the space, and they try to learn a model. So they forget about the time environment, but they tag it somehow. So they tag, I don't know, by the day or by the time, but they try to reduce the granularity of time, and by changing the feature space, they try to see and to detect if there's any correlation between whatever output you try. So if the output is energy consumption, and they try to find which important features are, and maybe important here is just that it's over the weekend or it's after 7 p.m. and they just add categorical features on top, and basically, so I know where you're coming from. You may say, well, but what I'm interested is much more a sequence of 10 minutes or 15 minutes, and you could do it. I mean, you can think about the time series as patches. So you think about an image, and then you compute, you just segment as in the line process, or you do obstruction, and then try to see which patterns are important for detecting this particular output here. And you can do some adaptation. So there's room for that. I've seen some work on the very first one where you do categorization of your time series, but you can also apply those techniques to your time series is basically now a spectrogram, and then you apply existing techniques. And I've seen some work from JP Morgan where they predict time series rather than considering the time series from a time series perspective. They consider as a picture, and then they use CNN on top. And then, so if you use CNN on top, you can apply techniques we just saw just before, and apply those and see which part of the picture is responsible for this particular output. So if you predict this to be, I don't know, a decreasing energy consumption, then just go and check it out. They have been doing quite some interesting work on time series, changing it as an image, doing predictions, and they show even better than state of the art on some particular data set. So you should check it out. So that's something I will, and that's been published, I think this year or last year. There's a conference on AI and finance. It's one of the first conference, was in 2021. It was in New York. I think it was published there. If you look it out, you can find it. Okay, so I think yeah, no worries and things. So, and if you don't find the paper, just send me a mail. I'll be more than happy just to give you the reference. I'll do that. Okay, another question from Sushma. So can the explanation be reasons? Which of the tools mentioned can provide the logic-based reasoning and the counterfactual explanations? Okay, I think the logic-based reasoning, so most of the work I covered was on machine learning, so which is correlation, which is not causation or causality. So there's no reasoning involved. So that means we find correlations, or the system try to find linear or non-linear correlations or combinations of features that end up in a result. So that means there is no reasoning per se. And then the counterfactual, I mean, what's really happening is again, there's no logic-based reasoning. The counterfactual is trying to see where is the loss function. So it's always considered a machine learning model. So if you have the loss functions, it's where the loss function is moving when adjusting a feature. So you fix all, and one is changing and you perturbating up and down, and then you try to see what's the impact of the loss function. And what they try to learn is well, the impact that you have, but on a very single level. So the counterfactual will say it's really by adjusting the loss functions accordingly. So in terms of reasoning, it's all analytical. There is no, I mean, you mentioned logics and reasoning, but there is no such thing. I mean, where there's logics, there's logics where you start using input with some logical representation. So if you start integrating if you have your labels describing your images or describing your pixels for a segmentation task, and if those labels have some semantic representation with some logic terms, with connections, that's where you could start exploring the reasoning dimensions. As far as I know, I haven't seen that work explored. I may have missed it. I won't be surprised, but I haven't seen it. And probably where you could see some of this work is on neurosymbolic reasoning techniques, because that's work where they combine neural-based techniques, so neural architectures, and symbolic techniques.
Sure.
Yeah, so that's probably where you could find some.
Thank you so much. Yeah, that's very helpful. I was hoping that probably a logic-based reasoning module or more that is more easily explainable. For example, in case of language understanding, I mean, it's not clear how that can be, how the present explainable, frameworks that you discussed during the tutorial, if they help towards bringing reasoning-based, logic-based explanations. Yeah, I thought that would be part of the explainable AI.
Yeah, I mean, there's some work on common sense reasoning and knowledge graph, and so it's come from I think the University of Washington in the Washington State, and they have been doing. I think it is. I forgot the name of the professor. She's very well known. She this very nice work on common sense reasoning and graph, and they do explore that avenue of knowledge and dialogue understanding or natural text understanding. So you should look it up. I think she gave a keynote, I think.
Actually, she was there in the NeurIPS. She gave a talk, and I think one of her papers, Yashin Choi, I guess. Is that right?
Yeah.
Okay. Thank you. This is super helpful. I think I can refer to some of her works and then get some intuition about it. Great tutorial, really. I couldn't have got this information, or wouldn't have learned about these many frameworks otherwise. Thank you.
Thank you. And again, on the text dimension, so there's definitely this work from the common sense reasoning dimension, but also from the maybe attention mechanisms. People have been using it, but they not in the reasoning sense. So you might get lost there. I think that the closest you already have the link for it. So yeah, and neurosymbolic reasoning, they definitely do address some tasks.
Yes, yeah, that's true. Yeah, I've been exploring. I mean, I've been working, studying about neurosymbolic reasoning, but I wasn't sure how to how to think of it from the explainable, concept. Based on the transformers, for example, transformer-based learning.
It's not an easy question. I know why you're struggling. It's because we build language model, and now we're asking to do language understanding. But given that the model base is not really understanding anything, so it's learning, right? So it's tricky. It's tricky. So you need to add some structure in there to make it. I mean, from my perspective, if you want to do proper understanding, you need to add some kind of structure, but not hard code it, something much more large scale structured, and then how you can use it. It's open questions. I think you're a very interesting open question.
Yeah, that's right. Yeah, I think that sounds really like a good direction to follow up on this question. Thank you very much.
Thank you, Sushma. Okay, so I have another question from Dini. Okay, so could you please explain the possible interpretable features of sequential recommendation data? So I think it's related to the previous questions on time series. So I think here it's the explanation will be So if you do have a time series and you try to predict the, let's say, the next stock price, so explanation might be coming from, so either it's only two-dimensional, so you have the stock price and there's a time series, and the only explanation is at some point during the evolution, that's the pattern that you get. So, and maybe, I don't know, if you have a drop a year ago and that you have it, maybe that's dropping again. So maybe that's what you should be looking at. So that's the features which is on time, and that's the concept that you get. So that's one thing. Another element is you categorize your time. So maybe you just start with an average per day, or maybe a few average per day, and try to see if there is I don't know, recurring patterns, and maybe the explanation might be coming from it's every day after the second, or and that's where you can get the recurrence, and that may learn the recurrence based, maybe. Or maybe you need to recombine with external data. So again, if you have this time series of stock price and you have the time, maybe that's maybe there's other data coming and interfering with the stock price. I don't know, worldwide situations, other stock price, and then you're adding more data. So you're adding more data and getting more features, and then you have a more classic problem of plenty of data. You're not only two-dimensional, you have many more, and then you try to find a model which combine the two, and if you use time series, you can use sequence-based architectures, and then trying to find maybe there's attention mechanism between to be learned, and maybe that's part of the explanation. So that's so maybe that's something that you can use. So that's something I will be considering, right? So what is your time series? Can you categorize some of the time, and you add that's adding features? Can you add more time? Can you add more data points? So that means maybe other stock price, maybe other things which do evaluate over time, and with this correlation that you didn't get, and maybe the explanation of something that you see now in a time series is not maybe due at all to what happens, because let's say you get a bad energy consumption now, high level of energy consumptions. Well, what if I say, okay, you get it every Friday at 6? That's, well, is it an explanation? I don't know. The explanation is what's really happening on Friday at 6, and that it's coming from something else, somewhere else, some other data. So, and then you may say, well, what maybe the other data I may be using? So maybe, I don't know, maybe a lot of people coming in, maybe traffic condition is correlated. Maybe a lot of people traveling before, and or they all stuck in during rush hours, and they're all occurring to be at their home at the same time, and that's the explanation. It depends what you're looking for in terms of explanation. Maybe having explanation, okay, that's every Friday at 6. Okay, that's enough. Maybe that's not, and then you need to add more evidence, and those evidence coming from the data, and then going back to the initial point about is the data important in explanation? Definitely. If you only have the time series data with 2 points, only 1 point evolving over time, the explanation is that point at different time. If you're adding more dimensions, the explanation is multidimensional. If you're adding wrong data, maybe you will learn wrong correlation. So always coming back to the data, always. Okay, thank you, Daphne. So I'll pause it again. So again, the session was for 4 hours. So I'll stay here if you have more questions. I know we were supposed to stay for 3 hours, so we went over 30 minutes, but they allocated 4 hours together. So we were, so if you have comments or questions or discussions, that's something we can have. I mean, that's we all miss the conference spirit. So if you want to discuss even some of the work you're doing, happy to do so. If you say, okay, we can do it, but don't record, I can stop the recording now. So I'll let you, yeah, I'll pause it now. And but again, thank you for everybody that stayed from the very beginning till the end. Well, I know I've been attending tutorials for that long, and that's a lot. That's a lot to ask, especially when there's only one person talking. If you don't like the style, that you might be suffering. But I try to change from presentation style to code. So hopefully, well, it was good. And for anybody that disappeared, and if you're listening now during the recording, thank you for having well, listen and attending the talk, even part of it. So yeah, so thank you for everybody. I'll stay here in the chat if you need, and feel free to ask more questions and access the different content that we provided.
Thank you.
Thank you, thank you, thank you. Sure, yeah, sure, William, you're welcome. So if you do have a challenge with the code, I tested it a few days ago, so it should be running with no problem. But if you do have, please ping. Okay, I'll stop the recording now.